Hi everyone. Is the audio video, is everything clear? Please tell me. So in this session, we will study 3NF BCNF decomposition, right? This is our last topic in the module 1. In the module 1, which is normalization, in that module, this is our last topic, lecture 16, that is 3NF BCNF decomposition. So algorithm we will see. If your relation is not in 3NF, if your relation is not in BCNF, then how can you decompose that relation into BCNF relation? How can you decompose that relation into 3NF relation? Okay, so these algorithms we will study. So the content of this lecture is BCNF decomposition, 3NF decomposition, and understanding dependency preservation. What is this dependency preservation? Again, we have already understood this. Okay, what dependency preservation means, that we have already understood, but we will just look at it once. We will revisit this topic once again. Okay, so anyway, so let's start now. And you can join the goclasses Telegram group. The username is gatecse_goclasses. For all your doubt discussions, this Telegram group you can join. Now let's see this BCNF decomposition. How can you decompose a relation into BCNF? What is the definition of BCNF that you already know? What is that? A relation is in BCNF if for all the non-trivial FD, the LHS must be a super key, right? If you have a non-trivial FD, okay, then this X must be a super key. This is the definition of BCNF that we already know. Okay, that we already know. Tell me the answer for this question. A relation with just two attributes. If you have a relation with only two attributes, can I say it is necessarily in BCNF? And the answer is yes. Okay, if you have two attributes, then it is mandatory that it will be in BCNF. Why? What is the reason? That we have already seen actually. What is the reason? If you have two attributes, for example, if your relation has two attributes, like for example, A, B, then what are the possible scenarios? There are four cases. Yes or no? There are four cases. The case one is there is no non-trivial FD. This is the case one, that there is no non-trivial FD. We have no non-trivial FD. In this situation, because you have no non-trivial FD, so automatically the relation is in BCNF because there is no BCNF violation. Correct? So if you have no non-trivial FD, if there is no non-trivial FD, then in this situation, what I will say? So basically, in this situation means A does not determine B and B does not determine A. Okay. So in this situation, I can say that relation will be in BCNF because there is no non-trivial FD. You have no non-trivial FD. So in this situation, it will be in BCNF because there is no BCNF violation. Okay. When the BCNF violation happens, can anyone tell me when the BCNF violation will happen? In which situation BCNF violation will happen? Your relation R is not in BCNF. Is not in BCNF. When can I say it is not in BCNF? It is not in BCNF if and only if there exists a non-trivial FD. Yes or no? There must exist a non-trivial FD. You must have at least one non-trivial FD. There must exist a non-trivial FD X determining A, where this X is not a super key. Where this X is not a super key. Okay, so this type of FD must, this type of non-trivial FD must exist. Correct? This type of non-trivial FD must exist. So if you have no non-trivial FD, then automatically your relation will be in BCNF. What is case 2? What is case 2? The case 2 is that A determines B. This is your FD. A determines B. Then here you can notice what is your candidate key. Your candidate key is A. Okay, and you can notice this is your only non-trivial FD. So this is in BCNF. So this is in BCNF because this A is a super key. Because this A is a super key. And what is the case number 3? The case number 3 is B determining A. The same situation will happen here also. And the case number 4, that is A determines B and B determines A. So in this situation, the candidate key will be A, B. A is also candidate key, B is also candidate key. Then in this situation also you have BCNF. And in this situation also you have BCNF. In this situation, your candidate key is B. Okay. So like this. So whatever case is there, case 1, case 2, case 3, case 4. 4 cases are there. In all the cases, this must be in BCNF. Okay, must be in BCNF. So if your relation has two attributes, if you have only two attributes, then your relation will definitely be in BCNF because 4 cases will be possible. Okay. And in each case, your relation is in BCNF. Okay. Now tell me, if I give you a set of relations, then okay. If I give you a particular relation, then you can say, for example, if I give you a particular relation, if I give you one relation, a particular relation, if I give a particular relation R, if I give, then you can say it is in BCNF, right? Okay, so you can say it is in BCNF or not in BCNF. You can say it is in BCNF or not BCNF. So either it will be in BCNF or it will not be in BCNF. If you have a particular relation, if you have one relation R, but if I give you a set of relations like R1, R2, R3, R4, 4 tables I have given to you. Okay, in this I have given to you 4 tables. When can you say that this system R, when can you say this system S is in BCNF? Tell me, when can you say this system S, this database is in BCNF? When can you say? Can you tell me? So you can say if all of them are in BCNF, right? So this must be in BCNF, this must be in BCNF, this must be in BCNF, and this also must be in BCNF. So all of them must be in BCNF. So I can say that if you have a database schema, okay, or I can say if you have a set of schema, R1, R2, and so on. So if you have a database, R1, R2, Rn, then this is in BCNF if each relation is in BCNF. Correct? Very simple. Each relation must be in BCNF. So I can say that a database is in BCNF if each relation is in BCNF. Now let's move on. Similarly, a database is in 3NF if each relation is in 3NF, right? A database, this is in 3NF if each relation is in 3NF. And similarly, a database is in 2NF if every relation is in 2NF. So very simple. Now you tell me, if a relation is not in BCNF, then how can you make it into BCNF? If your relation, you have a relation which is not in BCNF, then how can you make it into BCNF? Yes, we can do decompose. We can decompose into sub-relations which are BCNF. This is the idea, agree or not? So we can decompose R into sub-relations, which each of which is in BCNF. Each of them is in BCNF. Okay, each sub-relation must be in BCNF. That is the idea. Okay, so I can say this is the note. So if R is not in BCNF, then you can decompose R into sub-relations such that each sub-relation is in BCNF. Okay, now, so basically all you have to do, remember, all you have to do, just look at each sub-relation individually and check if they are in BCNF, right? Agree or not? Look at each sub-relation individually, okay, and check if they are in BCNF. This is what you have to check. Each relation you check, is it in BCNF? Now, you tell me this question. I am giving you a question and you tell me, is this BCNF decomposition? On your screen, you have ABCD, R, ABCD, and the functional dependency is ABCD. These are the functional dependency. You consider the decomposition. I am giving you a decomposition, which is R1, which is ABCD. So can I say this is BCNF decomposition? Can I say this is BCNF decomposition? Yes, the answer is yes, this is BCNF decomposition. Why? Because R2 is in BCNF. Because R2 is in BCNF. And you can notice R1 is also in BCNF, right? So R2 is in BCNF. R1 is also in BCNF. Why R2 is in BCNF? What is the reason R2 is in BCNF? Because only 2 attributes. So there is nothing to check. R1 has 2 attributes. So there is nothing to check. Agree or not? So R1, R2, they have two attributes. So nothing to check. They are in BCNF. So I can say, is this BCNF decomposition? Answer is yes. Is this good decomposition? This is BCNF decomposition, but is this good BCNF decomposition? Is this good BCNF decomposition? Is this good BCNF decomposition? Tell me. No, this is not even lossless. This is lossy. Can you notice? This is actually lossy. This decomposition is actually lossy. There is R1 intersection R2 is what? R1 intersection R2 is 5. There is nothing common. There is nothing common. So it is actually lossy. Yes or no? Can you notice? Is this clear to everyone? So this decomposition is actually lossy. Okay. Is this clear? This is lossy. So a lossy decomposition, can it be a good decomposition? If you have a decomposition which is lossy, it cannot be good. So you can clearly see that, I can say this is not a good BCNF decomposition. Can I say this? Not a good BCNF decomposition. Okay, but this is a BCNF decomposition. If someone asks you, is this BCNF decomposition? Answer is yes. Okay, to check if a decomposition is BCNF or not, what you will do? A given decomposition, I give you a decomposition. Okay, is this clear? Given decomposition, is it in BCNF? What you will do? You will check each individual table, each sub-relation you will check individually, you will check. But you can notice this decomposition is lossy. So this is definitely not a good BCNF decomposition. Is this clear? This is not a good BCNF decomposition. But this is a BCNF decomposition. Okay. Now, like you can see, this is from the Navate. If you have doubt, some students might be thinking that if it is lossy, it cannot be BCNF decomposition. We cannot call it BCNF decomposition, right? Yes or no? You might be thinking that if it is lossy, can we call it BCNF decomposition? Can we still call it BCNF decomposition? The answer is yes, we can call it, but that is not a good database design. Okay, this is not a good database design. You can call it because you can see from the Navate. This is the source from Navate. You can notice, for example, another goal is to have each individual relation is in BCNF. Okay, each individual relation in the decomposition must be in BCNF. However, this condition is not sufficient to guarantee a good database design. Is this clear? Tell me, is this clear to everyone? So remember, each individual relation must be in BCNF or 3NF. For example, in this example, R1 is in BCNF, R2 is in BCNF. So I can say that it is a BCNF decomposition, but it is not a good database design. For example, another example is also given. For example, you can notice a decomposition is given in which, okay, this table is in BCNF, but you can notice this table is in BCNF, but what is happening? This is a lossy decomposition. This is a lossy decomposition. Okay, so this is source from Navate. And similarly, you can also see from the Stack Overflow. This is the Stack Overflow link. In this, you can notice, do we consider the DCNF as decomposition as BCNF? If you have a decomposition, can you call it BCNF even if it is a lossy? Even if it is a lossy. So your decomposition is lossy. Can you still call it BCNF if your every sub-relation is in BCNF? The answer is yes. Basically, the answer is this. If you want to check a certain decomposition is in which normal form, then all you have to check is each component must be in that normal form. But of course, you can notice, this is not a good database design. Okay. So this is what I want to tell you. Understand the difference between these two questions. If I ask you to give me BCNF decomposition, will you give me lossy? Two questions, different two questions. You understand two questions. If I ask you to give me BCNF decomposition, will you give me lossy? Tell me. If I ask you to give me BCNF decomposition, will you give me lossy? The answer is no. You will not give lossy, yes or no? So if I ask you to give a BCNF decomposition, you must give a lossless. Agree or not? Yes or no? So if I ask you to give BCNF decomposition, you must give a lossless decomposition. But if I already give you a decomposition, given a decomposition, is it BCNF? Then what you will do? So here you will check every relation. In this, what you will do? In this, you will check every sub-relation. Okay, but here you will give me lossless. So understand the difference between these two questions. Is this point clear? So if I ask you to give me BCNF decomposition, then you must give lossless. You must give lossless. Okay. If I ask you to create a BCNF decomposition, you must create lossless. Okay. And of course, if possible, you also create dependency preserving. If possible, then you create dependency preserving if possible. Now, the another question is this. Given a BCNF decomposition, I already give you a BCNF decomposition. Is it in BCNF? Given a decomposition, is it BCNF? What you will do? In this case, you will just check the individual sub-relation, whether they are in BCNF or not. Tell me, did you understand the difference between these two? Is this clear? So if I ask you to create BCNF decomposition, I give you a relation and I tell you to create a BCNF decomposition, what you will do? You must give me lossless BCNF decomposition. And if possible, you give me dependency preserving also. Okay. Lossless is must. Lossless is mandatory. But if possible, you also give me dependency preserving decomposition. Okay. Yes or no? And the second point, if I give you a decomposition, and then I ask you, is this BCNF decomposition? Then what you will check? Then you will only check the individual subrelations. Then check the individual subrelation. Every subrelation you check individually. So these two questions, is this clear? The difference is clear. Tell me. Okay. Now let's move on. Now let's see. So remember, now finally, so while creating a BCNF decomposition, what you should do? If you are while creating BCNF decomposition, what you should do? While creating BCNF decomposition, if you do not care about lossless, then this will become a very trivial problem. Yes or no? I ask you to give me a decomposition. For example, let's assume R. You have a relation R. Let's assume a relation R. This is not in BCNF. Okay, not in BCNF. Let's assume. And I ask you to give me BCNF decomposition. Give a BCNF decomposition. Let's assume you become very smart. Okay. Give me a BCNF decomposition. Then you can notice that if I don't tell you give me lossless, then what will happen? If I don't tell you to give me lossless, then what will happen? You will just divide it into two attributes. Yes or no? Okay. If you don't care about lossless or lossy, if you don't care about lossless or lossy, if you don't care about lossy or lossless. Okay. So remember, if I don't tell you, or I can say if you don't care about lossy or lossless, then it is very trivial. Okay. Yes or no? Then it is very trivial. Then this question is nonsense. Can you notice? Yes or no? Then this question is nonsense, because what you will do? You will create two attributes. Two attributes. 1, 2. Two attributes. Another relation you can create two attributes. Another relation you can create two attributes. Okay. So two attributes you can create. Are you getting my point? Is this clear to everyone? So if you don't care about lossless or lossy, then this will become a nonsense problem. Agree or not? Do you agree this will become nonsense? If you don't care about lossless or lossy, then this question becomes nonsense. Is this clear? Please tell me. Okay, is this clear? Let me know. So this will become a nonsense question if you don't care about lossy or lossless. So you can notice very simple that if we do not care, okay, about lossless or lossy, then it will become a very trivial question, because what you will do, you can just divide the relation into sub-relations of two attributes. And this is given in the Ullmann also. The same thing is given in the Ullmann book also. In the Ullmann, you can notice that basically all you have to do, break down the relation into two attributes. Okay, and the result is surely in BCNF. However, this however word, okay, however, this decomposition will not be lossless. Yes or no? This type of decomposition will not be lossless. This condition number 2, that is lossless. So this type of decomposition may not be lossless. So this is the point I want to tell you, that okay, this is the final conclusion. What is the final conclusion? This is the final point I want to tell you. If okay, if I ask you to give me XNF decomposition, whatever, like 2NF, 3NF, BCNF, whatever, this X can be 2, this X can be 3, this X can be BC. So you can notice, if I ask you to give me 2NF, XNF, BCNF decomposition, what you will give me? Tell me. In this situation, what you will give me? Tell me. If I ask you to give me XNF decomposition, BCNF decomposition, 3NF decomposition, 2NF decomposition, then you will give me lossless. Then definitely you must give me lossless. Okay, you must give a lossless, and if possible, then you must give me dependency preserving. Agree or not? Agree or not? If possible, then you must give me dependency preserving also. But the another question is this: given a decomposition, is it XNF? Then what you will check? Given a decomposition, is it XNF? Then what you will check in this situation? Given a decomposition, is it XNF? In this situation, you will only check the individual table, right? Yes or no? You will just check the individual table, whether they are in XNF or not. This is the final conclusion that we have seen. Is this clear to everyone? Is there any confusion, or is this clear? This point is clear, or there any confusion? Do you have any confusion? Okay, now let's see the algorithm. Now let's see the BCNF decomposition algorithm. And this algorithm that we see, that will guarantee lossless. Is this clear? The algorithm that we will see now, the algorithm that we are going to see now, that will guarantee lossless decomposition. Is this clear? Okay. So now let's see the algorithm. But remember, this algorithm that I am going to tell you now, this algorithm will guarantee a lossless decomposition into BCNF subrelations. Okay. So what this algorithm is saying, with example, this concept will become clear. But what this algorithm is saying, very simple algorithm. What you do, you take the violation. This is your BCNF algorithm. Okay. And what it makes sure, what this algorithm is making sure, the algorithm that we will see, tell me what it will make sure. It will make sure that it will guarantee lossless. It will guarantee lossless. Okay, so it will guarantee lossless BCNF decomposition. Lossless BCNF decomposition, it will guarantee. Okay, what this algorithm is saying, this algorithm is very simple, that basically what you do, check, take any violation. If relation R is in, if R is already in BCNF, then what to do? If R is already in BCNF, then what to do? Tell me, then what to do? If R is already in BCNF, then nothing to do. Okay, then stop. Yes or no? Then stop. Then you can stop. There is nothing to do. And if R is not in BCNF, then what you do? If R is not in BCNF, in this situation, what to do? Very simple. You take a violation. What you do? You take a violation of BCNF. Any violation you can take. You take a violation of BCNF. You take this violation. For example, let's assume this is the violation. Okay, let's assume this is the violation. Then what it means? If it is a violation, then what it means? It simply means this is not a super key, right? It simply means this is not a super key. Agree? Because this is a violation. So you take any violation of BCNF. Let's assume this is the violation of BCNF. Then what you do? Then what you do? You find X plus. Okay, what you do? You find X plus. You find this X closure. Okay, this X closure, you make one table. Is this clear? This X closure, you make one table, and you make another table. You make another table where what you do? In the another table, what you do? From R, you remove this RHS alpha. Okay, this alpha you remove. R minus alpha. Is this point clear? And make sure that this is non-trivial. Make sure this is non-trivial. Okay, make sure this is non-trivial means their intersection must be 5. Okay, make sure their intersection is 5. Empty. Their intersection is empty. So this you make sure. Or basically, I can say that this from R you remove alpha, or if you want, I can say that from R you remove alpha, but you add X. Is this clear? Okay. So don't remove this X. Don't remove this X. Remove the alpha, but don't remove this X. Okay. Do not remove this X. So this is what you do. Okay. So find a violation of BCNF. Then you find X plus, and then you do this. The same algorithm we have done for 2NF. Very good. The same algorithm works for 2NF. But in the 2NF, what we do? In the 2NF, we check for 2NF violation. Yes or no? The same algorithm works for the 2NF. And then the 2NF, what we do? We check for 2NF violation. Violation of 2NF we check. And here we are checking for violation of BCNF. Okay, so the same algorithm. So what you do, very simple. You find this violation, find X plus, that will be your one relation R1. And another relation R2 will be from R, you remove the RHS. Don't remove the LHS. So remove the RHS, union X. Don't remove the LHS. So this is the simple point. Now let's see. With example, this concept will become clear. Okay. Now let's see this question. Do BCNF decomposition. Okay. Perform BCNF decomposition. Perform BCNF decomposition. So what you will do? First of all, is this in BCNF or not? What is your candidate key? You tell me what is the candidate key. C, A, C are not on RHS. So that is your candidate key. That is AC. So you can note this AC is a candidate key. So definitely this is violation. Do you agree? Definitely this is violation of BCNF. This is violation of BCNF. Why? The reason is very simple. This is non-trivial and this is a not super key. This is not super key, and definitely you can notice that this is non-trivial. Okay, this is a non-trivial. This FD is non-trivial FD. Now in this situation, what you will do? So you take this violation. Basically, this is a violation. So you can note this is a violation. So you take this violation, and what you will do? From this violation, what you will do? You will find A plus. Correct? You will find this A plus. You will find what is A plus? A plus is what? A plus is AB. This A plus will become your R1. Is this clear? This will become your R1. And what your R2 will be? R2 will be from R, from this relation R, you just remove the RHS. Okay. Don't remove the LHS. Don't remove the LHS. Remove the RHS. So what you will get? You will get A comma C. So you will get this R1 will be A comma B and R2 will be A comma C. So this decomposition you got. Is this clear? Let me know. Okay. So you will get A comma B, one table A comma B, and another table will be A comma C. So two tables you got. So finally, this is your BCNF decomposition. This R1 is A comma B and this R2 is A comma C. Now, do you have to check anything? Once you get two attributes, you don't have to check. Agree or not? There is nothing to check. This is guaranteed in BCNF. It is guaranteed that it is in BCNF, or it is also guaranteed that it is in BCNF. So this is a guarantee, right? And you can guarantee that it is in 3NF also. Sorry, it is lossless. You can guarantee it is lossless. Why? Why can you guarantee it is lossless? Why can you guarantee it is lossless? What is the guarantee? Tell me, what is the reason you can guarantee it is lossless? Anyone? Anyone want to tell me what is the guarantee that it will be lossless? Because the common thing, this LHS is the common thing, and that is a super key in R1. Agree or not? Yes or no? Very simple point I'm saying. Okay, very simple point I'm saying that in this algorithm, what you are doing, in this algorithm, you can notice that. So this is your algorithm. You have a relation R. Okay, this is your relation R, which is not in BCNF. Okay, so this relation R is not in BCNF. Now in this relation R, what you do? You find a violation. You find a violation which is, let's assume X determining alpha. Okay, or maybe X determining A or whatever. Okay, X determining A. Now what I'm saying, or maybe you can take alpha. So in this situation, what I'm saying that sorry, one more thing I want to tell you here. So you find X plus and you remove this X plus. Okay, actually you have to remove X plus, but you have to keep X. Okay, you have to remove X plus, you have to keep X. You have to remove X plus, you have to keep X. Is this point clear? Okay, you have to remove the X plus. Like this R1, completely this R1 you have to remove, but you have to keep this X. Okay, so what I'm saying here, for example, this is your violation. Let's assume X determining alpha, this is your violation. Okay, because this is a violation, so automatically this is non-trivial FD. Automatically this is a non-trivial FD, and automatically this is a not super key. Because this is a violation of BCNF. In this situation, what you will do? You will find, in this situation, you will find X plus, correct? This X plus you will find. And then you can notice in R1, what you will do? In R1, you will put X plus. So because you are putting X plus, so can I guarantee that X is a super key here? Can I guarantee X is a super key here? Agree or not? Can I guarantee X is a super key here? Right? Because you are putting X plus, so definitely X is a super key. Okay. And what your R2 will be? Your R2 will be from R, you remove this X plus. From the relation R, you remove this X plus and you don't remove X. So you can notice one thing, you can notice that this you can guarantee that this will be lossless. This will be lossless. Why? The reason is very simple. What is the intersection of R1 to intersection R2? That is exactly X. Okay, and you can notice this X can determine R1. Okay, and this X can determine R1. So this is a guarantee that it will be lossless. Is this clear? Is this clear that this will guarantee lossless? AC, and you can notice this is a BCNF and this is a lossless. So this is your answer. That's it. So very simple, this algorithm. Now let's see this. So tell me BCNF decomposition. Don't worry, we will take a lot of questions. A lot of questions we are going to take. So let's see BCNF decomposition. First of all, what is the candidate key? What is the candidate key? A comma D is not on RHS, so that will be the candidate key. So can you notice these are violation? Okay, can I say this is a violation? This is violation and this is also violation. Take any violation of your choice. This is also violation. This is also violation. Take any violation. Take a violation. Take a violation. Okay, any violation you can take. Take any violation. For example, let me take this violation. Is this clear? Let me take this violation. Now, in this violation, you can notice this is a violation. So let me take any violation. I am taking this violation. Now, in this violation, what you do? You find A plus. Correct? Find A plus. What is A plus? A plus is ABC. So find A plus, that will be ABC. Okay, so that is going to be ABC. So this ABC will become your R1. And what your R2 will become? R2 will be R minus this ABC. Okay, R will be R minus A plus. Correct? R minus A plus. But don't remove this A. So your R2, what your R2 will be? Your R2 will be AD. Correct? This will be your R2 and R1 will be A comma B comma C. Agree or not? Tell me, is this clear or not? So your R1 will be ABC. Your R2 will be AD. Now, this AD, can I say this AD is in BCNF? Only 2 attributes. So definitely it is in BCNF because only 2 attributes. So there is nothing to check. But we have to check R1. But we have to check. Remember, we have to check R1. What are the projected FDs of R1? In R1, what are the projected FDs? You find the projected FDs of R1. What are those? In R1, what are the projected FDs? So I can say that A determining B, C, that is projected FD. Agree or not? This is a projected FD, A determining B, C. So, okay, so this is the projected FD. So what is the candidate key? In this R1, what is the candidate key? That is A. So this is in BCNF. Agree or not? So you can notice this is not a violation. This is a super key. So this is a super key. This A is a super key. So I can say this R1 is in BCNF. So this is also in BCNF. This is also in BCNF. So finally you can stop here. So R2 BCNF, R1 BCNF. You can stop here. This is your answer. Okay, this is your BCNF decomposition. Now let's see the another question. Again, you do the BCNF decomposition. Take your copy pen. Again, you do the BCNF decomposition. So what you will do here in this question? Again, what is the candidate key? You tell me. What is the candidate key? So you can notice AD is the candidate key, right? This is the candidate key. So you can clearly see this is a violation because A is not a super key. Okay. And you can clearly see this is also a violation. Okay. You can clearly see this is also violation. This is violation 1. Let's call it violation 2. So you can call it violation 1. You can call it violation 2. So there are 2 violations. Both are violations. Now, what is the approach? Okay. Your method 1, what you can do? See, either you can take this violation first or you can take this violation first. Do you agree? Okay. So I can say method 1. In the method 1, what you do? You take violation 1. Either you can take violation 1 or you can take violation 2. So method 1, you take violation 1. If you take violation 1, then what will happen? This is your violation 1. So here you will find A plus. Again, you will find A plus. A plus is what? That is ABC. So this will become your R1. Correct? Okay. This will be your R1. And what your R2 will be? Your R2 will be very simple, that from R you remove this R1, but keep this A. But keep this A. Okay. From R you remove this R1. From R you remove this R1, but keep this A. But keep this A. So what your R2 will be? So the R2, you can notice the R2 will be basically A comma D. R2 will be A comma D, right? Okay, so finally what you will get here? In this situation, you go two relations. This is A comma D. There is 2 attributes. You only have 2 attributes, so there is nothing to check. So this is in BCNF because only 2 attributes are there. There is nothing to check. But you have to check R1. Let's check R1. Remember, you have to check this R1 ABC. What are the projected FDs? What are the projected FDs? Can anyone tell me? The projected FDs. You can notice A can determine B. You can notice A can determine B. B can determine C. So A can determine B. and B can determine C. These are the projected FDs. Correct? Yes or no? And of course, A can determine C also, but that is transitively given. A determines C also, but that is transitive. That is transitive. Okay, so it will be, I can say A determining B, B determining C. Now, what is the candidate key? What is the candidate key? Tell me. The candidate key is A. So because the candidate key is A, so I can say this is a violation. So this is again a violation. So now you repeat the same procedure. The same procedure you repeat. Is this clear? This is a violation. So the same procedure you will repeat. This is done. Okay, now you will repeat the same procedure. So take this violation. Take this violation B determining C. And what you will do? What is your next step? You will find B plus, right? Okay, so you will find B plus, that will be BC. This BC you can call R3. This BC you can call it R3. Okay, let me call it R3. You can call it R3. And what your R4 will be then? Then what your R4 will be? R4 will be from R1 you remove this B plus, but don't remove this B. But don't remove this B. So your R4 will be basically, I can say that it will be B, comma A. It will be B, comma A, comma B. So final your answer is what? Can anyone tell me what is the final answer? So the final answer is this. Final BCNF decomposition that you got. Okay, so the final BCNF decomposition that you will get is this. Okay, you can you got R1 which has AD, or I can say you got R2 which has AD, and you got R3 which has BC, and you got R4 which has AB. This is your answer. Is this clear? This is your answer. Okay. No, Yuvraj, it is not a mandatory thing. If you take different violation first, then you may get different BCNF decomposition. For this question, it will not happen. For this question, if you start with the violation 2, then also you will get the same decomposition. Let's see this. Okay, let's start with the violation 2. Okay, let's start with violation 2. Let me start with violation 2. Your violation 2 is this, B determining C. This is the violation 2. Okay, so this is your violation 2. Now you take this, then what you will do? You will find B plus. B plus will be BC. This is what you will do. You will find B plus. Now this will become your R1. Okay, and what your R2 will become? R2 will be basically from R you remove this B plus. Okay, but you keep this B. So finally I can say your R2 will be, I can say that will be ABD. This your R2 will be. Okay, now you have to check ABD. Now what you have to check? You also have to check ABD. So remember, now R1 is fine. Okay, R1 is BC. So there are two attributes. So this is definitely in BCNF. So there is nothing to check here. But let's check the R2. In R2, you have ABD. Okay, now in this ABD, what are the projected FDs? In this R2, what are the projected FDs? What are those? Projected FDs. What are those? So those are A determining B. This is the projected FD, right? Okay, A can determine B. So what is the candidate key? The candidate key is AD. So this is a violation. So this is a violation. Again, you can notice this is a violation because A is not a super key in R2. Okay, so in this situation, what you will do? You will take this violation. In this situation, just take this violation, and what you do? You find A plus. Okay, just find A plus. What your A plus will be? A plus will be AB. This AB you call, okay, this AB, what you can call it? You can call it R3. You can call it R3, and what your R4 will be? R4 will be from R2, you remove this A plus, but you keep this A. Okay, so for example, I can say your R2 will be basically, that will be AD. Okay, your R2 will be AD. So finally, you will get the same. In this particular question, you are getting the same, right? Yes or no? In this particular question, you are getting the same. So finally, your final, I can say final BCNF decomposition. Final BCNF decomposition, if you notice, so that will be, I can say that will be BC, AD, AB. Okay, that will be BC, AD, AB. Okay, but remember, it may happen if you take different order of violations first, okay, then you may get different BCNF decomposition. Is this clear to everyone? It may happen. Okay, so you may get different BCNF decomposition. You may get. You may get different BCNF decompositions. If you take, depending on the order of violations that we take, depending on the order of violations that we take, depending on the order of violations that we take. Okay, so depending on the order of violations, what is the order of violation that you are taking? Depending on that, you may get different decompositions. Okay, Nikhil is saying, can we start from any point and still get BCNF? If relation can be, can we start from any point and still get BCNF? Yes, every relation, whatever relation you take, Nikhil, every relation you can decompose into BCNF with lossless. This is guaranteed. Whatever relation you take, whatever relation you take, you can give a lossless BCNF decomposition. That is guaranteed. Like this algorithm that we have seen, this algorithm will give this guarantee. There are many algorithms. Let me tell you, this is not the only algorithm. Okay, first point. Okay, there are many algorithms. This algorithm I have taken from the Ullman book. Is this clear? This algorithm is taken from Ullman book. If you see the Korth book or Nawate book, if you notice, then they will give you some, their algorithm is little bit different. They don't take LHS closure. Are you getting my point? LHS, if you take Nawate or Korth, if you see their algorithm, if you study their algorithm, they will not take the closure of LHS. See, for the violation, we are taking the closure of LHS. Yes or no? For the violation, you have this violation. This is your violation. What we do? We are taking closure of LHS, right? Closure of LHS we are finding. We are putting the closure of LHS in a one table. Yes, closure of LHS we are putting in one table, right? But in Korth or Nawate, if you notice, in those books, if you notice, they will not take the closure. They will not take the closure. They will just put it in one table. So, are you getting my point? They will put it in one table. Directly they will put in one table. They will not take the closure of this. They will not find the closure of LHS. They will just take the LHS, RHS, and they will put in one table. Everything else is same. Everything else is same. Remember, is this clear? Everything else is same. But what they do, they don't find the closure. They take LHS, RHS. This is your violation. In the violation, take the LHS, RHS, and put in one table. That's it. Everything else is same. And another table will not have this, but it will have this. So two tables will be created. You put this violation in one table, and the another table will have this, will not have this. So this is the algorithm that they use. But can you observe? Our algorithm will definitely give you less number of relations. Yes or no? Our algorithm will give you, this algorithm, this Ullman algorithm, it will give you less number of relations. Less number of relations, because we are finding closure. Because we are finding the closure of LHS. This is your violation. We are finding the closure of LHS. So that is the reason we will get less number of relations. In the GATE exam, they will not ask you number of relations in the BCNF decomposition. In the test series, you will find. In the GATE exam, they will not ask you, because different algorithms, they will give you different BCNF decomposition. Is this point clear? Okay, if you apply the algorithm of Korth, algorithm of Nawate, algorithm of, if you apply the different algorithms, they will give you different BCNF decomposition. They will give you, some algorithm will give you 4 relations in the decomposition. Our algorithm will give you 3 relations in the decomposition. So remember, different algorithms, they can give you different number of relations in the final decomposition. In the GATE exam, they will not give you this type of question like find the number of relations in the BCNF decomposition. This type of question they will not give you. They will give you the decomposition and they will ask you, is this BCNF decomposition or not? Okay. A decomposition will be given to you and they will ask you, is this BCNF decomposition or not? Don't worry, all the GATE exam question we will solve. So automatically you will find out what question GATE exam is asking. Is this clear? What question gate exam is asking, that we will see. We will solve all the gate exam questions. But anyway, what I'm saying that you may get different BCNF decomposition depending on the order of violations that you take. Okay, let's move on. Like consider this example from the Ullman book. Okay, from Ullman DBMS book, consider this example. These functional dependencies are given to you. Let's solve this question first. First of all, what you do in the exam, they will give you this type of question. What you will do first? First, you will make abbreviations. Yes or no? First, you will make abbreviations. Correct? Agree or not? So don't use, okay, just make abbreviations. Like, okay, you can call it P and you can call it A. Precedent address. You can call it A. So finally, what are your FDs? What are your functional dependencies? These are basically, I can say, TY determines S determines P, and P determines A. These are your FDs. Is this in, look at this relation. So your relation is this. So your relation is this, that okay, TY is determining S, and S is determining P, and P is determining A. You tell me what are the candidate keys. Let me know. First, you tell me what are the candidate keys. You can notice T, Y, they are not on the RHS, and they can bring everything because T plus TY closure, if you find, that will be TYSPA. So you can notice the candidate key is a TY. Okay, this TY is the candidate key. So this relation, is this in BCNF? Is this in BCNF? This is a violation. This is a violation, and this is a violation. Correct? This is a violation, this is a violation. So two violations you got. Agree? Okay, we got two violations. But this is not a violation, right? This is not a violation. So we have two violations. Violation 1, violation 2. Let's call it violation 2. Let's call it violation 1. Now what you do? No, title year. TY determining S. TY determining S. Okay. So now you have two violations. Now what you do? Now you apply algorithm 1. What is the method 1? What is the method 1 you apply? So you apply violation. First you take violation 1. Let's start with violation 1. Let's start with violation 1. Let's start with this. So what you will get? This is your violation as determining P. So what you will find? You will find as closure. That will be what? That will be SPA. Okay. So this is your violation. So you will find this closure. You will get SPA. This SPA will become your table R1. This will become the table R1. Correct? So this is your table R1. What your R2 will be? R2 will be very simple. From the original table, you remove this S plus. You remove this S plus. Okay. But you don't remove this S. So from the original table, what you do? You remove basically remove this PA. From the original table, just remove this PA. So you will get TYS. Okay. This TYS you will get. Basically from the original table, you remove this PA. This PA you remove. So you will get this now what you will do? Now you have to check. Now what you have to do? You have to check. So your R1 is what? Your R1 is SPA. And your R2 is what? Your R2 is TYS. What are the projected FDs here? In this R1, what are the projected FDs? Tell me. In this R1, SPA, what are the projected FDs? You can notice S determining P, P determining A. These are the projected FDs. Nothing else. Okay, nothing else is a projected FD. These are the projected FD. You can check it out. Okay, and in this, what are the projected FDs? In this R2, what are the projected FDs? That is TY determining S, nothing else. TY determining S. So this is in BCNF, right? So this is in BCNF. So I can say this is the super key. This is the super key. So definitely this is in BCNF. You don't have to worry about R2. What about R1? In this R1, what is the candidate key? You find the candidate key. What is the candidate key? So here the candidate key is S. This S is the candidate key. So can you notice this is not in BCNF? So this R1 is not in BCNF. This R1 is not in BCNF. So what you will do? This is a violation. This is a violation. So what you are going to do? This is what you are going to do. Okay, forget about this. R2 is done. R2 is done. Forget about R2. Now what you will do in this situation? In this situation, you will take this violation. Okay, so take this violation and you find P plus. So P plus will be PA. This will become your R3. You can call it R3. So what your R4 will be? R4 will be basically you remove this A. Okay, you remove this A. So this SA will become your R3. That's it. So you can notice your final answer is what? So what will be the final answer? Final decomposition is basically, I can say, one is TYS. Final decomposition will be one is TYS, one is PA, one is SA. So this will be your final decomposition. Is this clear to everyone? Let me know. So this is the final decomposition. Okay, the starting from violation 2, will you get the same? Starting from violation 2, are you getting the same? If you start from violation 2, tell me. If you start from violation 2, will you get the same? So let's see method 2. Okay, start with violation 2. Let's start with violation 2. So your violation 2 is this P determining A. So what you do, you find P plus. So you find P plus, that will be PA. This will become your table R1, right? Okay, so what your table R2 will be? R2 will be basically just remove this A. Okay, just remove this A. This will be your table R2, TYSP. Okay, TYSP. This will be your table R2. Now, definitely only two attributes. So definitely this is in BCNF. So there is nothing to worry about it here. So one will be PA. One will be PA. There is nothing to check. Okay. Yes or no? Is this clear? Let me know. Oh, sorry. So this will be R4 will be, just remove this A. It will be SP. It will be SP. It will be SP. Okay, not SA. It will be SP. So you will get TYS, PA, SP. Okay. So in this, now you can notice that. So here one will be PA, and similarly you can check this. What are the, so again here also basically you will get the T. Okay, you have to divide this. Okay, you can check it out. This is not in BCNF. So TYS you will get, SP you will get. Okay, this is not in BCNF. This R2, this is not in BCNF. This is not in BCNF. So you will decompose this, and you will get one, you will get TYS, and one you will get SP. So actually you are in this question also you are getting the same. In this question also you are getting the same decomposition you are getting, the same final decomposition you are getting. Okay, I will find some example where you will get different decomposition depending on which FD you are taking first. Okay, I will take some example, but in this question also you are getting the same decomposition. Finally you are getting the same decomposition, but it is not necessary. Okay, you are getting the same decomposition finally, but it is not necessary. You may get different decomposition depending on the order of violation that you select. Okay, but anyway, this is your question now. So let's move on now. This question, can I give you as a homework? Can I give this question as a homework? Okay, you can check it out. You can do the BCNF decomposition. So now let's move on. Now, this is another question. Let's try this. Let's do this question. This is also another question about decomposition. Okay. Or maybe you can try this and maybe we can see it in the practice lecture. Tell me, yes or no? Or should we do this? Okay, this is a big question, so let's do this. More questions I have as a homework. But anyway, let me do this. See this question. What the question is saying that A, B, C, D, E, these are the attributes. Now the question is saying the exhibit, give a sequence of binary lossless joint decomposition into BCNF. You have to make sure that all of them are in BCNF. Okay, the decomposition such that it should be lossless and BCNF. So if you want this, if you want lossless BCNF, then which algorithm you can apply? Our algorithm you can apply, right? This lossless BCNF, if you want, then you can apply our algorithm. You can apply our algorithm, you can apply. That's it. Okay, so here the functional dependencies are given to you, and prove that each relation in your decomposition. First of all, is this in tell me, is this in BCNF? The relation is given to you A, B, C, D, E. And in the relation, you have A determining BC. Let me quickly do this. A determining BC, CD determining E. Okay. And you can notice B determining D, B determining D, E determining A. This is the question. Is this in BCNF? What are the candidate keys? Anyone? What are the candidate keys here? So you can check it out. A, B, C, D, E. Okay. So I think A will be a candidate key. A will give you everything. So A is a candidate key. A is going to give you everything. So now you don't consider A. Now do not consider A. E will also give you everything. Okay. So A will give you everything. E will also give you everything. What else? Now you can notice. So CD also will give you everything. And you can notice this BC, this will also give you everything. So these are the functional, these are the candidate keys. A, B, C, D, E. Okay. Is this in, so you can notice no non-prime attribute. So this is in 3NF, right? You can guarantee because every attribute is prime. So you can guarantee it is in 3NF, but it is in BCNF. Can I say it is not in BCNF? You can notice this is violation. This is your violation 1. Let me call it violation 1. And you can notice what is the another violation. So you can check it out. So, okay, this is the only violation. So that's it. So in this situation, what you can do? This is the only violation that you have. Then what you can do, very simple. So take this violation, B determining D, find B plus. So B plus will be BD. Okay, that's your B plus. So now your R1 will be this. You make one table here and your R2 will be from R, you remove this B plus. Okay, but don't remove this B. Basically just remove D. Okay, so you will get A, B, C, E. This will be your R2. Okay, your R2 will be A, B, C, E. Okay. Now, in this, what you do? So this is definitely in BCNF. This is definitely in BCNF. But can we say that this is in BCNF? Can we say this is in BCNF? What do you think? Can we say this is in BCNF? So you have to find the projected FDs. For the ABCE, you have to find the projected FDs. Okay. So what you do? Actually, you have to find the projected FDs. Remember, you have to find the projected FDs. These you have to find. Okay. So what are the projected FDs? You tell me. For example, what are the projected FDs? Like what A can determine? Of course, A will determine everything. A can determine everything. Like A can determine BCE. Okay. What B can determine? B actually cannot determine anything here. In this, okay, what C can determine? C cannot determine anything here. E can determine everything, of course. E can determine ABC. What else? So E can determine everything. And what BC can determine? What BC? Find BC plus here. So that will give you BCDE. So you can notice if you find BC plus, so that can determine AE. Okay, that can determine AE. So here in this question, actually, again, you can notice this is everything is a super key. Everything is a super key. So all of them are super key. All of them are actually super key. So I can say this is this relation. This is in BCNF. Okay, this relation is in BCNF because you find the projected FDs. The projected FD you find, and you can notice all of them are for all of them, LHS is super key. So definitely this R2 is a BCNF. R1 is BCNF. R2 is BCNF. This is your answer. Okay. Now let's move on. Now let's see this. So give some lossless BCNF decomposition. Can I give this question as a homework? Oh, actually, this is a nice question. This is a nice question. I want to make one point in this question. So let's see this. So what to do? Give some lossless BCNF decomposition. Can you give that? First of all, what are the candidate keys here in the relation R? What are the candidate keys? You can notice AB is a candidate key and AC is a candidate key. AB, AC. These are the candidate keys. Okay. Now you tell me this is a violation, right? Definitely. You can notice this is a violation. Okay. Because this is a violation and you want lossless BCNF. Only two things you want. You want lossless and BCNF. So this is a violation. So what you will do here? So in this situation, very simple that you will create one table, which is C plus is CB. So this you will create one table, you can call it R1, and another table R2 that will have AC. Okay, so definitely this is your relation. Okay, this is your decomposition. Yes or no? This is your decomposition R2, R1. This is the decomposition. Very simple. Now, okay, if I ask you another question, can you give me some, okay, I don't like, just give me some lossless and dependency preserving BCNF decomposition. Can you give me some? Tell me, can you give me some? Can you give me some lossless dependency preserving? Actually, in this question, whatever you try, you can never get. See, okay, very simple question, very simple observation you can make. You have AB determining C, and you have C determining B. You have AB determining C, and you have C determining B. If you want to preserve this, okay, and you can notice your relation R, that is your relation R. This is not in BCNF. You know your relation not in BCNF. Now, whatever you do, of course, you can give lossless BCNF, you can give, right? You can give lossless BCNF, that is fine. Okay, that you can give. Lossless BCNF decomposition you can give. There is no problem in that. Okay, possible. Lossless BCNF decomposition is always possible. Decomposition is always, that is always possible. Okay, so this is definitely possible. This is always possible. Okay, but what I'm asking, just tell me, to preserve this, a common sense you use. Okay, common sense you use, you tell me, to preserve this, if you want to preserve this, then can you see that they must be in the same table? Agree or not? If you want to preserve this, they must be in the same table. Okay, agree or not? So if you want to preserve this, to preserve this, A, B, C must be in the same table. Must be in single table. I can say must be in single table. And if you put them in the single table, then what is the problem? If you put them in the single table, then what is the problem? If you put them in the single table, then what is the problem? Then it is not in BCNF. Then it is not in BCNF. Then it is not in BCNF. If you put them in the single table, then not in BCNF. And if you don't put in the single table, then you can notice this is lost. So this dependency will be lost, whatever you do. Agree or not? So you can notice in this question, in this particular question, R, A, B, C, where A, B determines C and C determines B. In this question, okay, whatever you do, you cannot get these three things together. See, these three things together you can never get. Like you want BCNF also, you want lossless also, and you want dependency preserving also. These three things you want, right? Okay, these three things you cannot get together. For this relation, these three things can never happen together for this relation R. Okay, I can say for this R, these three things we can never achieve. These three we can never achieve. Agree or not? Tell me. These three we can never achieve together. We can never achieve them together. We can never achieve them together. Whatever algorithm you use, whatever you do, we can never achieve them together for this R. Is this clear to everyone? You want this also, you want this also, you want this also. We can never achieve them together for R. If we achieve this, then what we will lose? If we achieve this, if achieve this, then what we will lose? Tell me. Let me know. If we achieve this, okay, if we achieve this, then this is lost. Okay, then if we achieve this, then you can notice this is lost. If we achieve this, then this will be lost. Okay, let me know one more thing. Is it really lost? Is it really lost? Is it really lost? Is it really lost? No. So how to check it? So this is lost, but how to check it? By joining the tables, yes or no? So remember, When we say that, remember one very important point. When we say that your decomposition is not dependency preserving, then we say that some dependencies are lost. Yes or no? We say some FDs are lost. Agree? We say that some FDs are lost. But remember, these FDs we can still check by joining the tables. Okay? These FDs which are lost, we can still check by joining the tables. But we cannot check without joining the tables. Okay? By joining the tables, we can still check. But without joining the tables, we cannot check. So without joining the tables, they are lost. But if you join the tables, then you can check. Then you can enforce. Okay? So anyway, what I'm saying, these FDs are lost. And if you achieve these two, then what will be lost? If you achieve these, then what will be lost? If you achieve this, then this will be lost. Then we will not get this. Then this BCNF will be lost. Okay. So some trade-off we have to make. So you can notice for this question, no lossless dependency preserving decomposition is possible. Nothing exists. Okay. For this question. So you can notice for some relations, is this clear? For some relations, there are some relations for which there is no way to get all the three following at once. Are you getting my point? For some relations, there is no way to get all the three properties together. Like you want dependency preservation also, you want lossless also, and you want BCNF also. So these three things you cannot get together. For some relations, can I say for some relations you can get them? Can I say for some relations you can get them? For some relations we can get, yes or no? For some relations we can get. For some relations we can get, for some relation we cannot get. For some relations we can get. Is this point clear? So for some relations we can get, for some relations we cannot get. But if I say for all relations, okay, if I say for all relations we can get, if I say that for all relations we can get, then that will be false, right? Yes or no? If I say that for all relations you will get, then this statement will become false. So you can clearly see for all relations you can get all of them together. This statement will become false. Okay, so very simple. So for all relations, lossless BCNF you can always possible. Okay, very simple. So for all relations, lossless BCNF, it is always possible. But for some relations, this lossless dependency preserving BCNF, this does not exist. So this is your topic, BCNF decomposition. Now the next topic is 3NF decomposition. Let's check it. Okay, this is also small topic, but before that, let me see Nikhil doubt, what Nikhil is asking. For example, in this case, what should be? BCNF cannot be BCNF. Yes, of course it is BCNF decomposition. For example, if I give you a relation and I ask you to give me BCNF decomposition, just give me lossless BCNF. Is this clear? In the if I give you a relation, I ask you give me BCNF decomposition. What you should give me? You should give me lossless BCNF. Our algorithm will guarantee that. Yes or no? Our algorithm will guarantee that. And if possible, give me dependency preserving also. If dependency preserving possible, then give me dependency preserving also. But if dependency preserving is never possible, then just give me lossless BCNF. Is this point clear, Nikhil? Okay. If dependency preserving is possible, then give me that also. But if that is never possible, then give me lossless BCNF. Okay, don't worry, all the gate questions we will solve. So this question, this doubt will become more clear. Now, Mavit is asking, if we have unique FD violation, then will we have a unique lossless decomposition? Okay, see, Mavit, what happens is you are checking only the given set of FD. See, the given set of FD you are checking. You are not checking the F closure. Are you getting my point? Okay, you are checking the given set of FD. In the given set of FD, if there is one violation, then in the F plus there can be more than one. Are you getting my point? In the given set of FD, if you have one violation, then there can be more than one violation in the F plus. Okay, are you getting my point? So even if you decompose, if there is a single violation, let's assume in the given set of FD, there is single violation, then also you should check that after decomposition, you should definitely check that they must be BCNF. Mavit, is this point clear? Always check, are they in BCNF? Always check, is this in BCNF? Always check, is this in BCNF? Okay, is this point clear? Now, Ekta is saying BCNF decomposition may or may not dependency preserving, but see, BCNF decomposition may or may not lossless. Okay, BCNF decomposition may or may not lossless, but some lossless BCNF decomposition is always possible. These two statements, Ekta, understand these two statements. BCNF decomposition, it simply means just give me sub relations must be BCNF. I don't care about lossless or lossy. Are you getting my point? If I tell you BCNF decomposition, give me BCNF decomposition. Basically, I just want that sub relations must be in BCNF. I really don't care lossless or lossy. But if you give me lossy, that is a bad design. Okay, if you give me lossy, that is a bad design. But that is still BCNF decomposition. Is this point clear? So if you give me lossy, that is still a BCNF decomposition, but that is a bad design. Now this statement you read, BCNF lossless decomposition is always possible. Are you getting my point? It is always possible for all the relations. For every relation, it is always possible that you can have some lossless BCNF decomposition. Is this point clear to everyone? For every relation, it is always possible to get some lossless BCNF decomposition. Please tell me, did you get it? Now let's see the next algorithm, that is 3NF decomposition. And the algorithm that we will see, the name of this algorithm is synthesis algorithm. This is a popular algorithm. This was given by Philip Bernstein. So I have read this paper. This is an excellent paper. After the GATE exam, you can read this paper. Okay, this synthesis algorithm paper, the original research paper, in the paper in which he gave this algorithm, you can read this paper after the GATE exam. This is a very nice paper. But anyway, this algorithm, this synthesis algorithm is given in all the textbook. Nawate, Korth, Ullmann, whatever book you study. Okay, whether you study Nawate, whether you study Korth, Ullmann, okay, like whatever book you study, this algorithm you will find. The synthesis algorithm you will find. The name of the algorithm is synthesis algorithm. So for the 3NF decomposition, we will see this synthesis algorithm, and what this synthesis algorithm will guarantee. What this will guarantee? This will guarantee, remember, this will guarantee lossless as well as dependency preserving. This will guarantee lossless as well as dependency preserving. This synthesis algorithm that we will see. There are many more algorithms. Remember, you can have many more algorithms. Like, what is a very obvious algorithm for 3NF decomposition? What do you think? Give me one obvious algorithm for 3NF decomposition. One obvious algorithm. That is, just find BCNF. Just do the BCNF decomposition. Yes or no? Are just do the BCNF decomposition. That is one algorithm. But that algorithm will it guarantee dependency preservation? Will that algorithm guarantee dependency preservation? No. So that algorithm will not guarantee dependency preservation, but that algorithm is possible. Okay, that algorithm is possible, right? So you can notice that for the 3NF decomposition, what is very obvious algorithm? If I ask you, like if I ask you for 3NF decomposition, for 3NF decomposition, a very obvious algorithm, what that will come to your mind? A very obvious algorithm. A very obvious algorithm is BCNF decomposition algorithm. Yes or no? Just to do BCNF decomposition algorithm. Just do this, because if a relation is in BCNF, then it is also in 3NF, right? Yes or no? If a relation is already in BCNF, then it is also in 3NF, correct? So you can notice what to do. Just apply the BCNF decomposition algorithm. But this algorithm, okay, it will give you guarantee lossless. Yes or no? This algorithm will guarantee lossless 3NF decomposition is guaranteed. Okay, is it guaranteed? Yes or no? Using this algorithm, this is guaranteed. Okay, what I'm saying? I'm saying lossless 3NF decomposition is guaranteed, but may not be dependency preserving, right? May not be dependency preserving. But you can guarantee that, yes, I can guarantee lossless 3NF decomposition is guaranteed if you apply this algorithm. Is this point clear to everyone? This is a very obvious algorithm that will come to your mind. If you want to get 3NF decomposition, then what you do? Just get BCNF decomposition. Okay, because every BCNF relation is also in 3NF relation. So this algorithm, if you apply, then what you will get? You will definitely get lossless 3NF decomposition. You will get. Okay, guaranteed. This is guaranteed. But dependency preservation may not be guaranteed. Okay, but this algorithm, this synthesis algorithm, what this will do? What this synthesis algorithm will do? It will guarantee lossless also and dependency preservation also. So these two will be guaranteed. Okay, so this synthesis 3NF synthesis algorithm, this will give you a decomposition which will preserve the dependencies, which will give you lossless, okay, and it will give you 3NF. So this is a very, and what is this algorithm? This synthesis algorithm, what it actually does? See, this is a very different algorithm from 2NF BCNF. Okay, can you notice 2NF BCNF decomposition algorithm? They are very similar, right? This 2NF decomposition algo, this is very similar to, okay, I can say similar. This is very similar to BCNF decomposition algorithm, right? Correct? Decomposition algorithm. But this 3NF decomposition algorithm is very different. Is this point clear? This 3NF synthesis algorithm, this is very different. This 3NF synthesis algorithm is a very different. Is very different. In these two, can you notice you only focus on the violation? Okay, so yes, it will make sure. Okay, you always have dependency preserving 2NF decomposition. Dependency, you always have like some dependency preserving 2NF decomposition you can always find. Okay, some dependency preserving lossless 2NF decomposition you can always find. But what I'm saying that when I say similar, I want to say that this algorithm and this algorithm, they focus on the violation, right? Agree or not? This algorithm and this algorithm, they focus on violation, right? They focus on violation. They focus on violation. Agree or not? They focus on violation. Correct? They will focus on violation. But this algorithm, this 3NF synthesis algorithm, this is very different. Okay, this is very different. What this algorithm does? Okay, remember this is very different. So this is not same as those algorithms. So this is very different. This 3NF synthesis algorithm, what it does? You will see this is a very different algorithm. And I have seen on the internet many teachers what they do. You will also see this on the internet. Okay, you just check it out. Okay, what they will do? The same algorithm they will apply for 2NF decomposition, for 3NF decomposition, for BCNF decomposition. Okay, like this, they will focus on the violation. You can check it out on the internet, and they will make, okay, what announcement they will make before the video, they will make this announcement. तो दोस्तों अब हम देखेंगे एक बहुत ही इजी सी एल्गोरिथम हम सॉल्व करेंगे 5 क्वेश्चंस. ओके, इन 5 क्वेश्चंस के अंदर हम ये एक सिंपल से एल्गोरिथम लगाएंगे और दोस्तों आप सारे क्वेश्चन सॉल्व कर पाओगे. ओके, and then he will apply for those 5 questions, he will apply that wrong algorithm he will apply for those 5 questions. Okay, and that's it. He doesn't care. Let me tell you, you ask that teacher, okay, give me one standard resource where your algorithm is given. Okay, for 3NF, if anyone apply this algorithm, are you getting my point? For 3NF decomposition, for this 3NF decomposition, if anyone is applying this algorithm, like just focus on the violation, this is your violation, find the closure of this. Are you getting my point? You will see this. All the coaching institutes, they study from each other. Okay, you can check it out. On the internet, you can check it out. All these teachers, all these GOD teachers, GOD, all these GOD teachers, they study from each other. Okay, they don't have anything to do with the standard resources. What they will do? For 2NF, for 3NF, for BCNF, what they will do? They will apply the same algorithm. What they will do? This is the violation. They will find the closure of this. The same algorithm they will apply. Let me tell you what you do. For 3NF, when they do this, okay, only for 3NF, because for 2NF and BCNF it will work, right? Yes or no? For 3NF, for 2NF BCNF it will work. I've given you the screenshot of Ullman. But now what I'm saying, for 3NF, if they do this, then you put a comment. What comment you put? Put this comment: give me one standard resource where your algorithm is given. If you study Korth, Nawate, Ullman, Stanford, Berkeley, any standard resource, if you study, you will find synthesis algorithm. You will find. You will never find that dumb algorithm. Okay, but still you can notice, still there will be 1 million views on those videos. In the world, 1 million students are learning those wrong concepts. Almost every concept they make mistake. Almost in every concept, almost in every video they have mistake. Okay, like if I of course I cannot do that because I have institute. If I did not have Go classes, okay, if I was some, I can say freelancer or something, then I could have done this. For every video I could have told that this is wrong, this is wrong, this is wrong. And almost I can say that if there are 100 videos, almost 60 videos will turn out to be wrong. Almost 60 videos should be deleted. But still, million of the students, they are learning those wrong concepts. Okay, those wrong concepts, all the wrong concepts, million of students are learning. Okay, so that is the reason I request to all of you. This is my request to all of you. Share the Go classes resources, basically share the word of Go classes with all the students, so that at least you study the correct concept. At least you should study. See, if, okay, just to let me tell you why many students go to those videos. Can you tell me what is the reason? So many students, why they watch those videos? Because those videos are very easy. Those videos are very easy, very easy. A dumb student who does not have any knowledge, he can also understand. Okay, so those videos are very easy. And when you understand that, then you will think, okay, yeah, okay, he's a god. मेरे को concept समझ में आ गया, मेरे को ये नहीं आता था यार, मेरे को ना बीटेक में ये बिल्कुल नहीं आता था यार, मेरे को मतलब ये क्वेश्चन मेरे से होता ही नहीं था, अब मेरे को ये आ गया, ठीक है, ये टीचर तो गॉड है, ही इज अ गॉड, सब कुछ समझ में आ गया, पूरा सब्जेक्ट समझ में आ गया, पूरा एल्गोरिथम, पूरा कंप्यूटर ऑर्गेनाइजेशन, पूरा ऑपरेटिंग सिस्टम, पूरा डिजिटल लॉजिक समझ में आ गया, ये तो गॉड है, ये भगवान है. Actually, that Bhagwan, that God is not teaching you correct concepts. Most of the concepts, those are wrong concepts. But anyway, still students, they prefer those videos because those are easy videos. Okay, so anyway, I suggest you to prefer only quality videos. Just always prefer only the quality videos. Okay, of course, the rest of the world will keep watching those videos. It will always happen. Okay, 1 million views will definitely come. On the Go classes, 1 million views will never come, because very few students, they want, for example, on an NPTL, you check NPTL, okay, or you check, there are many good playlists on the internet. Okay, all the university playlists are there, like NPTL is there. You will never find million views, like 1 million, 2 million views, you will never find. Okay, because quality is not for everyone. Let me tell you, quality, that is not for everyone, but everyone should go for quality. If you are learning wrong concept, what is the benefit if you are understanding that? Yes or no? Wrong concept अगर आपको समझ में भी आ जाए तो भी क्या फायदा, और करेक्ट कॉन्सेप्ट अगर आपको थोड़ा समझ में आ रहा है तो भी बढ़िया. यस और नो? रॉन्ग कॉन्सेप्ट पूरा समझ में आ गया तो भी बकवास, और करेक्ट कॉन्सेप्ट थोड़ा समझ में आ गया, दैट इज ऑल्सो गुड. ओके, always you should go for quality lectures, like NPTEL lectures, MIT lectures, or Go classes lectures. I can guarantee all the Go classes lectures, because I give you a screenshot. I give you, like, whatever algorithm I tell you, I give you a screenshot from the standard resources. Okay, so basically, anyway, let's not talk about it more. So let's come to our topic. Our topic is 3NF decomposition algorithm. Okay, but anyway, final, this is my request to everyone. So on the Quora, like on Quora, whenever students are searching for Go classes, then on Quora they are not finding anything. The review of Go classes they are not finding on Quora. Okay, because yeah, okay, so very few students, they have written, I think 2 or 3 students have written Go classes review on Quora. Okay, so I request you everyone that on every platform, if it is possible, like maybe once in a month on every platform, you can write the review of Go classes. You can suggest Go classes to the gatecse students. Okay, at least study the correct concepts. Okay, so now anyway, let's come to our point. So this is your 3NF synthesis algorithm. This is very different algorithm. This synthesis algorithm, this is very different from these two algorithms. 2NF and BCNF, they focus on violation. Okay, but you can notice this this 3NF synthesis algorithm. What it does, first of all, it will find the minimal cover. What you do? See this step. First of all, you find the minimal cover. Is this point clear? First, you find the minimal cover. This is your first step. What is the second step? Okay, remember, this is very mandatory step. This first step, this is mandatory step. First, you find the minimal cover of FDs. Okay, this minimal cover, let's assume FDs are F. Okay, and let's assume this minimal cover, let me call it G. Are you getting my point? Let me call this minimal cover FC. Let me call it FC. Okay, now what you do in this FC, what you do in this minimal cover, what you do, you basically make sure, basically if LHS is common, then you put them, then you merge them. What you do, if LHS is common, if LHS is same, are you getting my point? If LHS is same, then you merge them. Then merge those FDs. Merge those FDs. If LHS is same, then you merge those FDs. Now, what you will get? Now, example, you will get this. Now, for example, you will get this type of FD. For example, let's assume you have X determining A1. Let's assume you have X determining A2. Okay, then what you will do with these two? What you will do? You will merge them. You will merge them into X determining A1, A2. Okay, you will merge into like this. Then what you will do? Don't check for violation. For every FD, you do this. Okay, this is important step. For every FD, what you do this. For every FD, not only for violation. Not only for violation, for every FD. Okay, is this clear? For every FD, whatever FD you have. For example, if you have this FD, okay, for every FD, what you do? Okay, so for every FD, what you do? You do this X, A1, A2, you make a table. Is this clear? You make a table. Are you getting my point? This is what you do. You make a table. Okay, for every FD, this is what you have to do. Not only for violation, not only for violation, for every FD, you have to do this. Okay, so the fourth step. What is the fourth step? So remember, this is very important step. For every FD, you are going to do this. Not only for violation, for every FD. If you have this FD, then you do this X, A1, A2, you put in R1. Okay, and the fourth step is this. This is the fourth step, that if none of the relation, from step 3, if none of the relations from step 3 contains a candidate key. Okay, yes or no? Is this clear? Like if none of the relations, this is the simple point. If none of the relations from step 3 contains some candidate key, contains a candidate key, then what you do? Then take any one candidate key, and make one relation for it, and make one separate relation for it. Separate relation for it. Is this clear? And there is one more step. What you can do? There is one more step. If one relation is superset of another, if you can basically you can delete. In the last step, you can delete some relations. You can delete some relations. Which relations you can delete? You can delete some relations. So for example, if R1 is superset of R2, are you getting my point? If R1 is superset of R2, then delete R2. Then delete R2. These are your steps. So these are the 5 steps. Is this clear? See, the first step, what is that? Find the minimal cover. This is the first step, FC. Now in the minimal cover, what you do? If LHS is same, then you merge those FDs. Like for example, here LHS is same, so you merge them into single. Now what you do? For every functional dependency, you create another relation. Is this point clear? For every functional dependency, you create another relation, separate relation you create. Then what is the step for? If none of the relations contain a candidate key, none of the relations, if they contain a candidate key, then take any one candidate key. Okay, is this clear? Like it is your choice, whatever. Take any one candidate key and make one separate relation for it, and delete some relations. Like if R1 is superset of R2, then delete R2. Okay, is this point clear? Let's see this example. Okay, let's see this example. So this is your relation R, A, B, C, D, E, and these are your functional dependency. Give me 3NF decomposition. This algorithm, what it will guarantee? This synthesis algorithm, what it will guarantee? It will guarantee lossless and dependency preserving. Okay, this is going to guarantee lossless and dependency preserving. So give me 3NF decomposition. What you will do? First of all, will you check violations? Array, will you check violations? Will you check violations for 3NF? Will you check violations? So you will not check violations. You will not check violations. You can directly apply this algorithm. But one thing I want to ask you, if your relation is already in 3NF, if your relation is already in 3NF, can you apply this algorithm? Can you apply this algorithm? You can still apply this algorithm. Array, because in this algorithm, can you notice? In this algorithm, nowhere we are checking for 3NF. Given relation is in 3NF or not, we are not even checking. Are you getting my point? Can you see in this algorithm? In this algorithm, we are not checking violations. We are not checking violations. We are not even checking your relation is in 3NF or not. Okay, is this point clear? So if your relation is already in 3NF, then also you can apply this algorithm, and it is possible you will get some other, some decomposition, some 3NF decomposition you will get. But if your relation is already in 3NF, then there is no need for this algorithm. You can just directly say that it is in 3NF, so you can stop. There is no need to apply this, but you can apply this. That is your choice. Okay, if your relation is already in 3NF, then if you want to apply this algorithm, you can do that. You will get a 3NF decomposition. Are you getting my point? You will get a 3NF decomposition. But if your relation is already in 3NF, then there is no need to apply this algorithm. You can directly keep it as it is. Okay, but then you have to check for 3NF, right? Yes or no? But then you have to check for 3NF or not. Okay, one thing, just focus on this thing. Checking given relation, you have a given relation, checking if it is in 3NF, it will take some time. Do you agree? It will take some time. From the computer point of view, it will take more time than applying this algorithm. Okay, see this, a very interesting scenario is happening here. If I give you a relation, and let's assume there are 20 attributes. So there are many functional dependencies, 20 attributes, and let's assume 100 functional dependencies are there. Then to check whether this relation is in 3NF or not, it will take some time. Agree? It will take some time. Okay, so if you check whether it is in 3NF or not, some time will be wasted, some time will be gone. Actually, you can apply this algorithm directly, and you can get 3NF decomposition in less time. Are you getting my point? Even if your relation is in 3NF, still, if you apply this algorithm in less time, this can give you 3NF decomposition. But if you check whether it is in 3NF or not, if you check that, if you do that checking will take more time. This algorithm will take less time. So that is the reason this algorithm is called synthesis algorithm. Are you getting my point? Why this algorithm is called synthesis? Why this algorithm is called synthesis? This is not called decomposition algorithm. Did you understand? This algorithm is not called decomposition algorithm. You are synthesizing 3NF. Okay, this interesting point, are you understanding? This algorithm is not called decomposition algorithm. This algorithm is called synthesizing algorithm. It does not care given relation is in 3NF or not. It does not care about the violations. You just give me the relation, I will give you the 3NF decomposition. I will synthesize 3NF. Whether it is in 3NF or not, I don't care. I will synthesize 3NF. Okay, so it is real. In the practically, what happens? Practically, when there are big attributes, 20 attributes, 30 attributes, 50 attributes, in those situations, checking for 3NF will take a lot of time, but this algorithm will take less time. So you can directly apply this algorithm. People don't even check 3NF or not. Is this clear? People don't even check 3NF or not. They will directly apply this algorithm, and this algorithm will give you 3NF decomposition with lossless dependency preserving. So this algorithm is very interesting. Do you agree? So that is the reason this algorithm is called synthesis algorithm. Okay. In all the books, in every standard book, you will find this algorithm. But this name, from where this name is coming, that is an interesting point that I told you. Okay. Now let's see. Anyway, let's apply this algorithm for this question. But let's check whether this is in 3NF or not. Is this in 3NF? Check this algorithm. This relation is in 3NF or not. First of all, this is your A, B, C, D, E, and these are your FDs. What are the candidate keys? What are the candidate keys? So in this, I can say AC. AC is a candidate key. So if you find AC closer, that will give you AC, B, D. Oh, E is also okay. So of course you must have E also. You must have E also, because E is also not on RHS. Okay, so this is the candidate key. Your candidate key is ACE, right? So your candidate key, that is ACE. This is the candidate key. So what are the non-prime attributes? What are the non-prime attributes? So the non-prime attributes are B, D. These are the non-prime attributes. So which is violation of 3NF? Can you not? Actually, you don't have to check violation, right? You just have to check is this in 3NF or not. So you can notice this is not in 3NF, right? Because A is not a super key and D is non-prime. So here you can notice not a super key and D is non-prime. D is non-prime. So here I can say that definitely this relation R is not in BCNF. I can say R not in 3NF. R not in 3NF. Okay. So now you don't have to care about the violations. Now don't find more violations. Is this clear? Is this point clear? No need to find violations. No need to find all violations. No need to find all violations. Because this algorithm does not care about violations. Agree? This algorithm will not care about algorithms violations. So now you can apply this 3NF synthesis algorithm. 3NF synthesis algorithm. You can apply this algorithm. So what you will get? First of all, you find the minimal cover. Okay, the step one. What is the step one? Find minimal cover. This is your step one. So don't forget about this step. You find the minimal cover of the FDs. Is this minimal cover? Is this B extraneous? Can I say this B is extraneous? Like for example, can I say A can determine C? In this A can determine C? No, A cannot determine C, right? Okay. Can B determine C? In this can B determine C? It cannot determine C. So I can say there is no extraneous attribute. Okay. Is this redundant? Can A determine D? No. Is this redundant? Can C determine B? No. Is this redundant? Can AB determine C? No. So you can notice this is already in minimal cover. Yes or no? Already minimal cover. Okay. What is the next step? If you already minimal cover, then what is the next step? So you have minimal cover. You already have minimal cover. What is the step number 2? Anyone? Step number 2. Step number 2 is what? Okay, just if you have common, if you have common LHS, then merge them. There is no common LHS, right? If common LHS, merge. If common LHS, then merge. But there is no common LHS, so you don't have to worry about it. What is the step number 3? What is the step number 3? Now you do this. So one relation will be created for ABC. One relation will be created for CB. One relation will be created for AD. This is a very easy algorithm. Can you notice? Can you notice this is a very easy algorithm? This is extremely easy algorithm. Even if you implement this, if you want to implement, you can implement. This is a very easy algorithm. What is the step number 4? The step number 3 is this. Any of them, do they contain candidate key? Your candidate key is, you already know. Your candidate key is ABE. This is your candidate key. Sorry, ACE. Sorry. What is your candidate key? What was the candidate key? That was wait a second. In this question, what was the candidate key? Like A, B, C, B, C, D, E, A, E. Okay, so in this question, what was the candidate key? In this question, the candidate key was actually, it was ACE also, and it was ABE also. Okay, so these were the candidate keys. ACE, ABE. Okay, ACE, ABE. These are the candidate keys. So anyway, these are the two candidate keys you can notice. So your ACE, ABE, these are the candidate keys. Okay, is there any relation which is containing them? Is there any relation which contains candidate key? Is there any relation which contains? Does any relation contain candidate key? Tell me. Does any relation of step 3 contains some candidate key? Contains some candidate key? The answer is no, right? Okay, the answer is no, because this also does not contain candidate key. This also does not contain candidate key. This also does not contain candidate key. So they do not contain candidate key. So the answer will be no. So in this situation, what you will do? So add any one of them, right? Add one of them, like ABE, ACE. Add one of them. So make one table for one candidate key. Make one table. Okay, add one table. Okay, I can say, so add one table for any one candidate key. For any one candidate key. Is this point clear? So in the step 4, your answer will be what? So after the step 4, you will get what? So your relation will be this. In the step 4, you will get ABC, CB, AD. Okay, so you will get ABC, CB, AD, and also you can add one of them. One of them you can add. Like for example, maybe let me add ACE. Let me add AC. Okay, now you tell me. Okay, what is the step 4? What is the step 5? Remove some relations. Remove some relations. Remove some relations. What are the relations that you can remove? I can remove this CB, right? This CB I can remove. Correct? Okay, because you can notice ABC is already superset of CB. So this CB I can remove. Okay, so this CB can be removed. So your final answer will be ABC, AD, ACE. This is your final answer. This is your 3NF decomposition. Okay, and remember, this is, you don't have to check. This is guaranteed to be lossless. This is guaranteed to be dependency preserving. You don't even have to check it. There is a guarantee that it will be lossless and it will be dependency preserving. So did you understand 3NF synthesis algorithm? Extremely simple algorithm. Can you notice? If you implement this, it is very simple. If you implement this in the computer, in your computer, if you write a program for this, it is extremely simple. Now, that interesting point that I want to tell you, why we call it synthesis algorithm. Okay, that was an interesting point, right? Why this algorithm is called 3NF synthesis algorithm. Like, why we call it synthesis algorithm? Okay, so from where this word is coming, like synthesis, 3NF synthesis algorithm. So the reason I told you, what is the reason? See, the reason is very simple, because checking a relation is in 3NF. Checking a given relation is in 3NF or not. Is in 3NF or not. Is more expensive. Okay, is more time taking than this algorithm. Is more time taking than this algorithm. Are you getting this point? So if you want to check whether a relation is 3NF or not, that is actually more time taking. Okay, remember, that is actually more time taking than this algorithm. Okay, so what people do, this is what people do. Okay, this is what people do. So if, okay, so if you have So let's assume you have a relation. So assume you have a relation. So this is what people do actually. So assume you have a relation with say 50 attributes. Okay, with 50 attributes. Is this clear? So let's assume you have a relation with 50 attributes. And what you want? Tell me. You want 3NF. You want 3NF database. And let's assume you want 3NF database. Okay, is this clear? This is what you want. This is what you desire. So you want 3NF database. Now you have two ways. What are the two ways? Tell me, you have two ways. What are those? What are those two ways? Tell me. Can anyone tell me what are the two ways? Either you check if you are already in 3NF or not. Correct? Okay, so there are two ways. One way is check if we are already in 3NF. Check if we are already in 3NF. Already in 3NF or not. Okay. And what is another method where you don't even have to check it? Where you don't even have to check it, or directly, yes or no, directly apply this algorithm. Correct? Directly apply 3NF synthesis algorithm. 3NF synthesis algorithm. Regardless your initial relation is in 3NF or not. Correct? Regardless. Okay, regardless of given relation is 3NF or not. Okay, so regardless of that, you just apply this. Okay, so you check this 3NF or not. If not, then you apply this algorithm. If not, okay, if not, then apply this algorithm. Then apply synthesis algorithm. Correct? Okay, so these are the two ways. And have you seen this type of situation in your real life? In your real life, have you seen this type of situation that something is more expensive? Like something is more expensive, you can directly do, like you don't even have to check. Have you seen this type of situation in your real life? Let me give you example. Let me give you example. For example, let's assume you have a small pen. Let's assume you have a 5 rupees pen. Okay, let me assume. Actually, this is not 5 rupees pen. So let me assume you have a 5 rupees pen. Okay, and or maybe 2 rupees pen. You know, now in the older days there were 2 rupees pen, right? Okay, 2 rupees pen, very nice pen. So you can notice. Let's assume this is a 2 rupees pen. Will you waste your time? Okay, how much ink is there? Okay, you will open this and you will check how much ink is there. Will you waste that time? Okay, will you waste that time? No, because it is just a 2 rupees pen, you will purchase another. Are you getting my point? Without checking whether it contains ink or not, without checking whether it is working or not, open it and do all these things. What you can do? You can just directly purchase another, or you can borrow from your friend and never give. Okay, if you are giving the pen back to your friend, definitely you are not true friends, right? Okay, to the true friends, we never give the pen back. Okay, this is a universal law. Okay, so you can notice that very simple. So you don't have to waste your time to check whether this pen has ink or not, because it is just a 2 rupees pen. Okay, so you will open it, you will check it. Okay, some things you will do. Instead, what you can do, you can just take another pen that is less expensive. Just directly take another pen. From your friend, you can take your, okay, give me your pen. That's it. Okay, so very simple. So this type of situation maybe you have seen in your real life. Okay, in the real life, this type of situation maybe you have seen where one operation is expensive. Okay, one operation is expensive, you can just directly do the second operation. So similarly here, you can notice that checking whether a relation is in 3NF or not. Okay, your relation, check if it is in 3NF or not. It is already in 3NF or not. This is already expensive operation. Yes or no? It is more time taking operation. So what you can do, you can, regardless of it is in 3NF or not, you can directly apply this algorithm. This synthesis algorithm you can directly apply, and this algorithm will give you your 3NF decomposition. Okay, so this is the reason this is called synthesis algorithm. Is this clear to everyone? Why this is called synthesis algorithm? Is this point clear? So this algorithm does not care whether the initial relation is in 3NF or not. Okay, so you can notice, yes or no? So So this 3NF synthesis algorithm does not care if initial relation is in 3NF or not. Okay, it does not care if the initial relation is in 3NF or not. It will just directly synthesize. Okay, yes or no? It can directly synthesize. It can directly apply. So like this you can do. I hope this point is clear. Okay, so let's see this question. Okay, now if a relation is in BCNF, can it bring a relation to 3NF, not in BCNF? If your relation is already in BCNF and then you apply this algorithm, your relation is already in BCNF. You tell me, Nikhil, what do you think? You tell me, Nikhil. If your relation is in BCNF, how may or may not, just see what this algorithm is doing. If your relation is already in BCNF and then you apply this algorithm, let's assume. Okay, this is Nikhil. This is the doubt of Nikhil. Nikhil is asking this doubt. So that if your relation is, if R is already in BCNF, okay, and then let's assume you apply this synthesis algorithm. Okay, then you apply synthesis algorithm. Then you apply 3NF synthesis algorithm. Can it take you out of BCNF? Can it take you out of BCNF? Okay, can it make you, can you make you non-BCNF? Can you make database non-BCNF? Can it make some relation non-BCNF? Some relation non-BCNF? Anyone want to tell me why the answer is no? Anyone want to tell me why the answer is no? Why the answer is no? Tell me, what is the reason the answer is no? Because your already relation is BCNF, right? Okay, so the answer will be no. The answer will be no, because you are already saying that your relation is in BCNF. So you are already saying that your relation is in BCNF. It means in the minimal cover, what will happen? Whether you take minimal cover or whatever, right? Okay, you take minimal cover or whatever you do, okay, in the minimal cover, there will be minimal cover. You will find the minimal cover. So you are already in BCNF. So if you find the minimal cover, in the minimal cover, whatever is there, this X will be super key, right? Yes or no? Agree or not, Nikhil? This X will be a super key. So finally, what you will do? You will create a relation. So when you apply the synthesis algorithm, then what will happen? If you apply the synthesis algorithm, then what will happen? This X alpha will be one relation. This X alpha will be one relation. Okay, so it will be in BCNF. So it will be in BCNF, right? Yes or no? Is this clear? So okay, if you are already in BCNF and then you apply this algorithm, you will still remain in BCNF. Is this clear? Let me know. Okay. So in the minimal cover, you will do this in the minimal cover. Okay. Is this point clear, Nikhil? So if you are already in BCNF, then you apply this synthesis algorithm, you will stay in BCNF. There is no problem. It can it make you non-BCNF? Can it make you non-BCNF? The answer is no. It cannot make you non-BCNF. You will still remain in the BCNF. Okay. Let's see this question quickly. Let's see this. Yes, this is what I'm saying. Every relation you can break into lossless BCNF. Every relation you can break into lossless BCNF decomposition. You can do lossless BCNF decomposition. That is always possible. Now read this question. This is a very nice question. What is the reason this is a very nice question? Because you can notice what we have seen so far. You have seen so far that for every relation, see, this is what we have seen so far. For all relations, see, these things I have to write in capitals because people don't focus on these words. Yes or no? Can you notice people? Okay, have you seen this in your last 6 or 8 months? People don't focus on these words. Like you are writing all here, but still people will ask doubts. Okay, so anyway, you can check it out. Okay, so anyway, what I'm saying, for all relations, it is always possible. It is always possible. What is always possible? What is always possible? For all relations, it is always possible. What is always possible? This is always possible that you have 3NF and you have lossless and okay, it is like this type of decomposition is always possible. Okay, it is always possible that that there is a decomposition, okay, where it is lossless and dependency preserving. Okay, and dependency preserving. So for all relations, it is always possible that there is this type of decomposition is always possible. Agree? This type of decomposition is always possible. It is always possible for all the relation. It is always possible. Okay, such a decomposition always possible. And what about BCNF? If I remove this 3NF here and if I put BCNF here, then this statement you have to remove, because it is not always possible. Of course, sometimes it is possible. Sometimes it is possible, but this such decomposition is always possible. Okay, such a decomposition. Now you can notice this question is very nice. This is from a standard university, from a standard resource. This question has been taken. Why this question is nice? Can you tell me? Actually, the reason this question is nice is because the question is only asking for BCNF lossless decomposition. Agree? Yes or no? The question is only asking for BCNF lossless decomposition, and the question is only asking for 3NF decomposition, which is both of them. Yes or no? It is also asking for 3NF decomposition, which is both of them. Okay, so this is the reason. This is actually very good question. Okay, because the question maker knows, the professor, the person who has created this question, he knows that for BCNF we can definitely create this, but dependency preservation may or may not be possible. Dependency preservation may happen or may not happen. Similarly, for the 3NF, this lossless and dependency preservation, this is always possible. Okay, so this is the reason this question is very nice. Okay, I don't remember the resource of this question, Mavit. Actually, this question I have taken from my old I can say database from the last 5 years. From my old database, this question I have taken. Okay, so I did not. I think this question I took from the CHAG. Okay, so I don't remember what is the source of this question. Originally, I took this question from the CHAG website. Okay. Anyway, let's see this. So anyway, let's solve this question. This we have already done. Okay, now let's see this second question. So what the question is asking, first you find the minimal cover and then you give a decomposition into 3NF. So can you do that? Let's see this. Okay, let's do this. Take your copy pen. FD set is given. In the FD set you have A determining BCD, then BC determining DE, then B determining D, and then D determining A. Okay. Now let's see this. Nikhil is very fast, extremely fast, Nikhil. Okay. So let's see this. So you can notice this is your relation ABCDEF. ABCDEF. Your relation is ABCDEF. Remember. So what was your relation? First of all, in the relation, what you do? You find the candidate key. Okay. Before anything else, you find the candidate key, because we need candidate key for 3NF decomposition, right? Okay. For 3NF decomposition, we need candidate key. So first you find the candidate key in this. A, B, C, D, E, F. So you can notice A, B, C, D, E. F must be there. F must be part of every candidate key. Okay. So I can say, for example, what about AF? What it can create? It can create A, B, C, D, F. It can create A, B, C, D, F, and then you can notice BC can create D, E. So it can create everything. So I can say one candidate key is AF. Okay. And you can notice automatically DF will also be a candidate key because D can determine A. Because D can determine A, so DF also will be a candidate key. And because B can determine F, so B can determine D, so BF also will be a candidate key. So AF, DF, BF, all of them are candidate key. Is there any other candidate key? Do we have any other candidate key? Tell me. Like ABD, ABD. Okay. So what about CF? No. And what about EF? No. What about CEF? What about CEF? That also no. So I think only these are the candidate keys. You can check it out. Okay. These are enough. These are all the candidate keys. So now you have all the candidate keys, that is AF, BF, DF. Okay. The given relation, is this in BCNF? Sorry, 3NF. Given relation, what do you think? The given R is in 3NF or not? Given R. You can notice, for example, you can check it out. Is this in, so for example, look at this. BC determining E. Look at this, BC determining E. Okay, just look at given R, BC determining E. This is not a super key, right? Correct? This is not super key. This is not super key, and this is non-prime. And this is non-prime. So given R is definitely, I can say, not 3NF. Not in 3NF. So this given relation is actually not in 3NF. Okay, now let's see this. So first we will do the minimal cover. So first you find the minimal cover, that is your step 1. So your step 1 is find minimal cover. Find minimal cover. So what you will get? Find the minimal cover. What you will get? What answer you will get here? First you tell me, is there any extra attribute here? Extraneous on LHS. Extraneous on LHS. Only one attribute is there. So there is no extra attribute on LHS. Is there any extra attribute here? No. Is there any extra attribute here? Okay, let's check this. Can B determine D? Actually, okay, one more thing I told you. Do you remember? One more thing I told you before finding minimal cover. What was that? Before finding minimal cover, RHS must have single attribute. Okay, so for a moment, let's assume they have single attribute. For a moment, let me assume they have single attribute. So you tell me, can actually what you should do? You should divide them. So BC determining D, BC determining E. Okay, you should do that. Actually, you should do that. Is this clear? Similarly, A determining B, A determining C, and A determining D. So, okay, so that is fine. Now you tell me. So you can notice here, what is extra? Can I say B determine D? Can B determine D? Yes, B can determine D, right? Okay, B can determine D. Actually, you this complete, so you can remove C. Actually, you can remove this complete thing, right? Because B can determine D. So this complete thing you can remove. You can notice B can determine D. B can determine D. So C is unnecessary. C is extraneous. C is extraneous. Now these are duplicate. B determine D, B determine D. So these are duplicate. So I can say that definitely this is gone. Okay, I can say this is definitely gone. Now forget about this. Now don't consider this. This is gone. What about this one here? Can B determine E? No. Can C determine E? No. Okay. Now, okay. What about this? If I remove this, can D determine A? No. D cannot determine A. If I remove this, can B determine D? If I remove this, can B determine D? No, B cannot determine D. Okay. Next, you can notice, if I remove this, can BC determine E? No, it cannot determine. Okay. If I remove this, can A determine B? Can A determine B? No, A cannot determine B. And if I remove this, can A determine D? Can A determine D? Can A determine D? If I remove this, can A determine D? Yes. Yes, 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 yes. If I remove this, A can still determine D because A will determine B, B will determine D. So this is gone. Correct? This is gone. If I remove A determining C, then I cannot remove that. Okay, I cannot remove this. So I cannot remove them. Okay. So I think this is yes or no. Baki, all the remaining are mandatory. So your finally your minimal cover will be this. And what you do, you merge the step two. What the step two says? A determine C, A determine B, BC determine E, B determine D, D determine A. What your step two is? What your step two is? So this you can remove. What the step two? Step two is you can merge the same LHS. If you have, you can merge them, like BC determining A, like B determining D, and like D determining A. What is your step three? What is your step three? Step three is for every FD you create another table. Step three is one table for ABC, one table for BCE, one table for BD, one table for AD. Okay, so you can create this. Yes or no? This is your step three. What is step four? So now you got ABC, BCE, BD. Okay, from the step three, what you got from the step three? So the step three is giving you ABC. It is giving you ABC. It is giving you BCE. It is giving you BD. And it is giving you AD. Okay, now you tell me what are the AF, BF, DF. Okay, any of them, do they contain step three relation? Any step three relation? Tell me, any step three relation contains any candidate key? The answer is no. The answer is no. Okay, so what you have to do? You have to add the step number. Okay, so what you have to do? So you have to add a relation, add any one candidate key, add any one candidate key as a new relation, Okay, so what you will get? You will get this. So ABC will be 1, BCE will be 1, BD will be 1, AD will be 1, and AF will be 1. Okay, AF will be 1. Now, of course, you can have different 3NF decomposition. Yuvraj, similar to BCNF. In the BCNF also, you can have many BCNF decomposition. Similarly, you can have many 3NF decomposition. You can have many different 3NF decomposition. Can you merge something? Can you remove some relations? Can you remove some relations? The answer is not possible. Here it is not possible, right? Okay, here removing some relations is not possible. So your final answer will be what? So your final answer will be this. Of course, you can get many different relations you can get. Yes, minimal cover is also not unique. See, first of all, minimal cover is not unique. The second point, you can choose any candidate key to add. Yes or no? There are many steps. The first point, even minimal cover is not unique. You can have many different minimal cover. So minimal cover can be different. Okay, which minimal cover you are taking? Second point, you can add any candidate key as a separate relation. Choose any candidate key as a separate relation. So basically, ultimately, you can very easily see that you can get many different 3NF decompositions. Is this clear? You can get many different 3NF decompositions. Okay, this is your chapter. Please tell me, did you get everything? See, in a very crystal clear manner, I've tried to tell you all the points. And can I give this question as a homework? Okay, so take this question as a homework. Okay. So now read this. Is this statement true? For all relations, it is always possible to get the following three properties, right? Yes or no? To get the following three properties. Recoverability of information means lossless. Okay, this is true. What about this statement? So you can notice, for all relations, lossless 3NF is always possible. Lossless 3NF is always possible, of course. Okay. Who can give you this lossless 3NF? If you only want lossless 3NF, then who can give you this? You don't even need synthesis algorithm. If you want lossless 3NF, then the BCNF algorithm can give you. Agree or not? Then the BCNF algorithm also can give you. And you can notice for all relations, lossless dependency preserving 3NF is always possible. Okay, so this is the idea. So this is the concept, and we have seen everything. This question also I'm giving you as a homework, but the solution is also on the next page. See these questions, how many questions are there? 5 questions. So these questions also I'm giving you as a homework, but the solutions are also here. These are the solutions. These are the solutions. Okay, and these are the solutions. So you can check it out. And finally, this is the summary, XNF decomposition summary. What is the summary? This is the summary. See, decomposition to BCNF. We have an algorithm. There is an algorithm for lossless BCNF, right? There is algorithm for lossless BCNF decomposition. And decomposition to 3NF. There is algorithm for lossless and dependency preserving 3NF decomposition. Okay, so all these points, you can read it. So you can notice, and one thing about redundancy, I told you that in 4NF, we don't have any redundancy. We don't have redundancy due to FD. We don't have redundancy due to MVD. That we have already seen, right? In the 4NF, redundancy due to MVD is not there. And redundancy due to FD is not even in BCNF. BCNF does not have it. Can you lose FD? Can you lose FD in 3NF? Okay, no. So because you can create some dependency preserving decomposition, but in BCNF you may lose FDs. Okay, so these are points. Even BCNF schema may have redundancy, but BCNF is 100% free from redundancies caused by FDs. Okay, so these are some points. And one last point I want to tell you, actually, I already told you. So the question I want to ask you, do you understand dependency preservation? Okay, this question I want to ask you, do you really understand dependency preservation? Because most of the students, they by heart it. Okay, they just, okay, yeah, projected FD I will find, F1, F2, F3. For every relation, I will find the projected FD. Then I will take their union, and then I will check, is it equivalent to the original FD? Yes or no? That is the method. Agree? That is the method. Correct or not? Basically, for every relation, you find the projected FD, you take their union, and the union should be equivalent to the original relation FD. Okay, then we can say that, yeah, our decomposition is a dependency preserving. But that is the method. You keep the method separate. What is the logic? Tell me what it means when we say that dependencies are preserved. Can anyone tell me what it means when we say that in the decomposition dependencies are preserved? Yes, it means that you don't need to join any tables to enforce the FD. To enforce any FD, to check any FD, you don't need to join any two tables. You never have to join any two tables. It's like this. It's like this. If every table, basically every table, it takes care of itself. You don't need two tables to merge. Agree or not? Every table will take care of itself. You take care of yourself. You take care of yourself. You take care of yourself. If every table takes care of themselves, this table takes care of its own FD. This table takes care of this own FD. This table takes care of its own FD. Every house takes care of their own issues. Then all the FDs will be checked. Then all the FDs will be enforced. So there is no need to join. Are you getting my point? Yes or no? So this is the meaning. When we say that some FDs, when we say that decomposition is dependency preserving, it simply means that there is no need to join two tables to enforce any FD. There is no need to join any two tables to make sure that FD exists. Okay, there is no need to join any two tables. And when we say that dependency preservation is not there, when we say that FDs are lost, what it means? FDs are lost. What it means? It means that now if you want to enforce the FD, then what you will have to do? Can you do that? FDs are lost. Some FDs are lost. Now can you enforce the FD. Now, can you make sure that FD exists? Can you enforce the FD? Yes, you can enforce the FD, but more expensive operation you need to perform, that is join operation. You have to join the tables. You have to join some tables. Yes or no? Whatever FD you want to enforce, for that FD, what you have to do? Okay, you have to join some tables to enforce that FD. To make sure that that FD exists, you have to join some tables. Individual table cannot ensure all FDs. Okay, so sometimes for some FDs, you have to perform an expensive operation, that is the join operation. Okay, let's see this more understanding. Okay, some doubts are there, yes or no? Definitely some doubts are there. Agree? It looks like not clear. Like yeah, I got it 60-70%, but not clear, right? Something like that. Is anyone feeling that? Is anyone feeling that? Okay, I got the idea, but I'm not actually visualizing it. I cannot actually visualize it, right? Okay, so let me, of course, that is my responsibility, that you visualize everything, that you completely understand everything. So let's see this dependency preservation decomposition revisited, because actually we have already seen this. So that is the reason I'm calling it revisited. Now let's see this. First of all, read this question and tell me what is the answer. Read this question and tell me the answer. A decomposition D of relation R with FD set F is a dependency preserving. Okay, then what we can say? Each dependency of F can be enforced by dealing with individual relations. By dealing with individual relations. Yes, that's the correct, right? Okay. Each dependency of F can be enforced by combining one or more relations, but may not enforce by the individual relation. You can enforce by individual relation, right? Okay, so option B is not correct. We need to join all relations to enforce. This is also not correct. So dependency preservation, what it simply means, this dependency preservation, it simply means that you can enforce all the FDs. Each FD you can enforce, okay, by only handling the individual relations. The individual relations are enough to enforce all the FDs. You don't need to join any two tables. Any two tables you don't need to join. There is no need to join any two tables. Individual relations can can make sure that your FD exists. Okay, but anyway, let's understand this clearly. In a crystal clear manner, let's understand this. Do you truly understand what does dependency preserving decomposition means? Okay, we have already studied this. We have already seen this, but let's revisit. Let's see this question. Okay, you look at this question. Is this a dependency preserving? Okay, so what you are doing, this is your relation R, and you are decomposing into these two. In the decomposed database, okay, in the decomposed database, can deletion create problem? Okay, when you delete any table, do you need to check any dependency? This is my question. While deletion, do we ever need to verify any FD violation? Tell me this question. While deletion, this is a simple question I'm asking. While deletion, do we ever need to verify any FD violation? If you delete some data, can you violate some FD? Just tell me a simple point I'm asking. If you delete some data, can you violate some FD? You can never violate FD, right? Okay, so you can never violate FD. A very simple point. If you are deleting a data, you can never violate FD. So very simple. So, okay, deletion can never violate FD. Deletion can never violate FD. So deletion never triggers the FD checking. Is this clear? Deletion never triggers FD checking. Okay, so this never triggers FD checking. So who will make sure? So then who? Then I can say while insertion or modification, either insertion or modification, right? So I can say while either you insert the data or you edit the data, or you modify the data, or you modify the data. So while insertion or modify the data, okay, yes. Do we ever need to? Yes, we need to verify that FD is violated or not. Correct? In this situation, we have to make sure that FD is not violated. Okay, now this question I'm asking, a very simple question. Read this question carefully. Now the question is saying that this decomposition is given to you, and I'm asking, in the decomposed database, while insertion or deletion, because deletion will never create FD violation, while insertion or modification of data, how to enforce A determining C? Do we have to join? Do we have to join? You tell me. Do we have to join the tables? A simple question. Do we have to join the tables? Do we have to join the tables? A simple question. Can we only care about individual relations without joining them? Can we only care about individual relations without joining them? Can we enforce it without joining them? Okay, question is very simple. You have a relation R, which is ABC, and in this what you have? You have that A determines B, B determines C, and A determines C. Okay, now what you are doing? You are doing this decomposition. You are doing this decomposition. Okay, one you have AB and another you have BC. C. Okay, now. C. If you want to enforce this, okay, can you enforce this? These are the FDs of the original database, right? These are the FDs of the original database. Now you tell me, to enforce this, what you will do? To enforce this on the decomposed. Okay, this is the decomposed. This is the decomposition. This is the decomposition. Tell me. If you want to enforce this, then this relation can enforce, yes or no? So this relation I can say can enforce. This relation can enforce this, right? And what about this? I can say that this relation can enforce this. Okay, because here you have A determining B. Here you have, and what about this? Do we have to join? Are you getting my point? Do we have to do the natural join? Do we have to do the natural join? Here you have A determining B. Here you have A determining B. Here you have B determining C. Here you have B determining C. Where do we have A determining C? Where do we have A determining C? Tell me. Anyone? Where do we have A determining C? Yes, transitively. We don't have to join. Transitively, it is already enforced. Remember, this is already enforced. This is already enforced. Okay. In individual relations. In individual relations. By transitivity. There is no need to join. To enforce this, there is no need to join. See what I'm saying. Please understand this, what I'm saying. Okay. See, this is your table. Now you have this table AB. And this is your table BC. Okay. In this table, what this table is taking care? Tell me what this table is taking care. This table is taking care of A determining B, right? This is taking care of A determining B. This is taking care of what? This is taking care of what? This is taking care of B determining C. So this is taking care of B determining C, and this is taking care of. Now. So now let's see. I want to make sure that this type of data must not come. Agree? Do you agree that this type of data must not come? Do you agree this type of data must not come? Because A should determine C. A should determine C. So, okay, can you guarantee without joining? Can you make sure this will not happen? Can you guarantee this will not happen without joining? Can you guarantee? Tell me. Can you guarantee it will never happen? It will never happen without joining? Okay, it will never happen. Can you guarantee it will never happen in R1 or I can say in the database. Okay, it will never happen in database. Without joining. Can you guarantee? Yes, you can guarantee, because you can notice. Okay, just tell me, if this happens, then what should happen? Array, very simple point, a very simple point. If this happens, then what should happen? Like by chance, if this happens, then what should happen? By chance, if this happens, let's assume, by chance, if this tuple matches with this tuple matches with this, then what should happen? Then this B must be same, correct? Then this B must be same, agree or not? Do you agree? Tell me, do you agree? Do you agree that if this happen, if this should happen, then what should happen? If this should happen, then this should match with this should match with this. Do you agree? Correct? Very simple point. This should match with this should match with this. But if this is matching with this, then you can notice, if this is 1 1, then because A determining B, so it should be 4 4. You cannot keep them different. And similarly, now, can they be same? Can they be same? You tell me, can they be same? No, they cannot be same, because B determines C. So they cannot be same. Cannot be same. Cannot be same. So here they must be different. Okay, they must be different. Now, so this situation can never happen. So now you can notice that this situation can never happen, right? So this situation can never happen. I can say this situation can never happen. This situation can never happen. And why this situation is never happening? Because it is doing its work and it is doing its work. Do you agree? This R1 is doing its work and R2 doing its work. So that is the reason transitively this will never happen. There is no need to join R1, R2. We don't have to join R1, R2. R1 should do its work. R2 should do its work. Okay. Then transitively this work automatically will happen. Is this clear? So this is what I'm saying. A very simple point. So here A determining B, here B determining C. Okay, so they automatically, I can say they automatically, or I can say transitively, enforce, they transitively enforce A determining C. Do you agree? No need to join. Okay, to enforce this, no need to join. If you want to enforce this, to enforce it, no need to join any tables. Correct? One more example I want to take, this last example. Consider this, AB determining C, C determining B. Okay, and decomposition I'm giving you BC, AC. How can you enforce this? Tell me. A very simple point. This is not dependency preservation. Actually, in this question, you can note this was dependency preserving, right? If you notice, this was actually dependency preserving. This was actually dependency preserving decomposition. So that is the reason you don't have to join. There is no need to join. Now, in this question, you can clearly see that this question is not dependency preserving. This is not dependency preserving. But still, this FD we can enforce, right? This FD we can enforce here. Okay, so this is your table. So you have a relation R where you have ABC and your FD is AB determining C, C determining B. Now what you are doing? You are doing the decomposition and you are saying, okay, AC here, BC here. See, this can make sure, this can enforce this, right? Okay, can enforce. Agree? So there is no problem here. There is no problem here. This can enforce this. But how to enforce this? Okay, this was lost. Agree or not? This was lost. Now you tell me, this type of data should come or not? A simple question I'm asking. AB, for example, this type of data should come or not? Like ABC, 1 2 1 2 3 4. This type of data should come or not? This type of data should come or not? You tell me this point. This type of data should not come. This type of data should not come. But can we stop this data on without joining the tables? Like, okay, only by this relation, by R1, R2, individually, without joining them, can they stop this data? Tell me, can they stop this data if you don't join them? If you don't join them, then can they stop this data? So you can notice there is no one who can stop this data. Agree? Here 1314 can come. Do you agree or not? Here 1314 can come, right? Okay. Of course, this data is legal. This is a valid data here. 1314 can come. Okay. What else? Here in the BC, can this data come? For example, I'm asking, can this data come? 3-2 and 4-2. Can this data come? Tell me. Yes, C determine B, right? Yes. So C is determining B. So you can notice this data can come here. This data can come here. If this data is coming here, can you notice this data has come? Can you notice this data has come? Yes or no? Can you notice this data has come? Possible to exist. Possible to exist. Yes or no? Possible to occur. Possible to occur. Did you notice this? Please tell me. Very nice point. Very simple point. Very nice point. What I'm saying? Now you can notice this data has occurred. Because on based of C, you will join them. So this will join with this. So 1, 2, 3. And you can notice this will join with this. So 1, 2, 4. So this data is possible to occur if we only check individual table. Agree or not? If we only care about individual table. Yes or no? If we only care about individual table. Or I can say if we only check individual tables. If we only check individual tables, this data is possible to come. Now, is this crystal clear? Please tell me. Are lossless or lossy has nothing to do with this dependency preservation. Nikhil, lossless or lossy has nothing to do with dependency preservation. I am talking about dependency preservation. I am talking about dependency preservation. I am not talking about lossless or lossy. It is lossless. This decomposition is lossless. But I am talking about dependency preservation. You tell me, in the original database, should this data come? In your original database R, is this data possible? Tell me. In the original database R, is this data possible? This is not possible. What I'm saying, I am saying that can you stop this data after decomposition? Are you getting my point, Nikhil? After decomposition, can you stop this data? After decomposition, see, after decomposition, it is possible to occur if you only check individual tables. You can still stop this data. How? You can still stop this data. What do you need to do? If you want to make sure this does not happen, what do you need to do? To make sure it doesn't happen, what do you need to do? To make sure it doesn't happen, okay, I can say you have to merge the tables, correct? Okay, to make sure it doesn't happen, for every insertion, you have to join R1, R2. For every insertion, you have to join R1, R2. You have to first join R1, R2. Is this clear? Let me know. For every insertion, you have to join R1, R2. You have to join R1, R2 first. Now, is this crystal clear? Is this point clear? Our decomposition is lossless. I am not saying that this was already there. Nick, see, you are thinking this in the wrong direction. I am not going from R to R1, R2. I am going from R1, R2 to R. See, are you getting my point? I am not going from R to R1, R. It's not. This is lossless. It is lossless. What I'm saying. Just think about this. Okay, just think about this. A simple point. You have a database. Okay, in that database, like for example, I am the school principal. And I want, you are the designer. You are the database designer. I am the school principal. and I want you to enforce that AB should determine C. Are you getting my point? Did you get it? I want you to enforce AB should determine C. I'm telling you, I will give you money only if AB should determine C. Okay, that is what I'm saying. Did you get it? I will give you money if AB should determine C. Then I will give you money. I am also telling you that I want BCNF. So two things I'm telling you. I'm telling you, okay, that I'm telling you to enforce AB determining C. You enforce this. Now, if you make two tables, now forget about, there is no original table. Just for a moment, let's assume there is no original table R ABC. In your database, you create two tables. You are creating the database. You create two tables. One is AB, one is BC. Is this clear? Okay, you are creating two tables. See this. Okay, you are creating AC, you are creating BC. You are creating two tables. Now, in these two tables, can I insert data such that this will eventually happen? This is my question. Mavit, Nikhil, did you get it? In these two tables, can I insert data in such a way that eventually this will happen? Did you really get it? Did you really get it? Tell me. Please tell me, did you really get it? Nikhil, got it? Is there any doubt or not? Nikhil, Mavit, Ekta, anyone? Akash, any doubt? Yuvraj? So what I'm saying? Okay, so very simple point I'm saying. Forget about this. Now this is not there. In the same database, can you have this and this? In the same database, can you ever have this? Will you ever have this? In the same database, will you have this and this? No. Once you do the decomposition, this is gone. This is gone. Okay, don't think about this. Okay, don't think about this. This is gone. Don't think about this. So let this is gone. So this is gone. Don't think about this. Now in your database, you have this. Now your database has this. This original was gone. Now your database has this. And now you can notice that now I cannot enforce this, right? Agree or not? Okay, if I have only this and this, I don't have the original table. Now I cannot enforce this. Of course, I can enforce this, but if I want to enforce this, then what I need to do? To make sure it doesn't happen, for every insertion, I have to join. Before every insertion, I have to join. Agree? Before every insertion, I have to join. Yes or no? For every insertion, for every modification, first you have to join the tables. Okay? To make sure it doesn't happen, to make sure this type of situation doesn't happen, for every insertion, for every modification, you have to join the tables first. Without joining the tables, you cannot enforce it. Okay? So I can say if you join them, joining them can enforce it. Joining them before every insertion, every modification. Before every insertion, comma modification. Okay? So this is what I'm saying. Forget about this. This is your database. So this is what I'm saying, that joining them before every insertion of or modification can enforce AB determining C. Okay, so join and infer. So if you have, so this is the disadvantage. See, so this is the final point that I want to tell you, that if your decomposition is not dependency preserving, if your decomposition is not dependency preserving, then something heavy will happen, some expensive operation will happen. Then before every insertion or modification, what you will have to do, or I can say before, depends, basically before insertion or deletion, sorry, before insertion or modification, we may have to join two or more tables to enforce some FDs. Okay, but it will not happen for every insertion, right? Yes or no? See, it will not happen for every insertion because some FDs are already enforced. Some FDs are already enforced. Like for example, this FD is already enforced. Okay, so I can say that insertion of deletion, we may have to, okay, for insertion of deletion, we may have to join two or more tables to enforce some FDs. This is your final point. So now this is your question. Now, can you read this question? And now you can tell me, now did you understand this? The same question I am revisiting again. The same question I am revisiting again. The same question revisiting again. A decomposition is dependency preserving. What it means? Now, did you understand this clearly? Please tell me. How much did you understand? 100%, 90%, 80%? Tell me. Crystal clear or not? Please tell me. Dependency preservation, not dependency preservation. What it actually means. What it actually means, that is clear or not? Okay. So now you can notice, if you have dependency preserving decomposition, if your decomposition is already dependency preserving, then I can say, what I can say? I can say each dependency can be enforced by dealing with individual table. Okay. So your answer will be option A. Very simple. So option A will be answer. These are not the answer. Answer will be option A. And what about this question? Which statement is true? Two statements are given to you. Which statement is true? Not dependency preserving. Not dependency preserving. Then each dependency can be enforced by dealing with individual table. No. Okay. Yes. Each dependency can be enforced by dealing with individual table. No. Some dependencies may be enforced by dealing with individual table. This is possible, right? Some may be enforced by individual table. Okay. Some may be enforced by individual table. What about this question? Tell me the answer now. Not dependency preserving. Some dependencies need join of one or more relations to enforce them. This is also correct. Option C is also correct. All dependencies need join of one or more table? No. Okay, the answer. So, crystal clear? Tell me, whatever we have seen. So finally, which normal form is preferred? Tell me. Nikhil, transitively they are enforced. You don't have to enforce them separately. Transitively they are already enforced. The transitive dependencies, they are already enforced. Are you getting my point? For example, okay, like if you have transitive relation, okay, like for example, let's assume I teach you, you teach someone else. Okay, then I can say, let's assume my content, let's assume I'm teaching you my content. Let's assume the same content you teach to some other student. Then I can say that that student is learning from my content, right? Yes or no? I can say that student is learning from my content. So you tell me, this is automatically done, right? Because I am teaching you, you teaching him. So this is automatically done. This transitive thing is automatically done. We don't need to do anything else for this. Do I have to teach that student? Tell me, do I have to teach that student? No. Transitively, I am teaching that student. I am teaching you, you are teaching him. Transitively, I am teaching that student. Okay, something like that. Okay, are you getting the idea? So transitive dependency, you don't have to do anything. That is automatically enforced. Okay, is this clear? So transitive dependencies are automatically enforced. You just enforce this, you enforce this. Okay, like it's like you enforce this, you enforce this. Then automatically this transitive thing is already enforced. You just take care of this, you take care of this. Don't worry about this transitive. That is transitively enforced. Okay, so tell me, which normal form is overall nice and preferred? Which normal form we prefer? Do we prefer BCNF? Tell me, do we really prefer BCNF? Do we really prefer BCNF? We don't prefer BCNF. Why? What is the reason? Because in the BCNF, dependency preservation may not happen. Some FDs are lost. And to check, then what you have to do? Just think about it. If you create a BCNF decomposition, some FDs are lost. Now, before every insertion or every deletion, sorry, before insertion or modification, you have to join them. So there is no benefit. The BCNF is giving you some benefit. Okay, the BCNF is giving you some benefit, but now what you have to do? Before insertion or modification, whenever you want to do some insertion, whenever you want to do some modification, before that, you have to join some tables. That join will take some time. So overall, it will become very expensive, right? So that is the reason overall 3NF is preferred. Okay, 3NF has some redundancy, but okay, it has less redundancy than 2NF. 2NF has more redundancy, 3NF has less redundancy, and BCNF has zero redundancy due to FDs. Due to functional dependency, BCNF has zero and 3NF has some, but that is fine. Some redundancy is fine, agree or not? As long as it is saving you time, 3NF will save a lot of time. So 3NF will save a lot of time, BCNF will waste a lot of time. Okay, BCNF will save you some redundancy, 3NF will give you some redundancy, but overall some redundancy plus less time. So that is good. So ultimately 3NF is preferred. Okay, so ultimately remember overall which is preferred. So the answer is 3NF. This is ultimately preferred. This is ultimately the best normal form. You can call it best normal form. Okay, and we have already seen why. This is your chapter, and this question I give you as a homework. So that's it. All the slides are over. Everything is over. So this is your chapter. Okay. Any other doubt? Mavit is asking, sir, if our algorithm of decomposition doesn't produce, then relation not able to. Mavit, actually, I will have to check it. But actually, there's no information available on the internet. I tried to find it. Will the BCNF decomposition algorithm, will it give dependency preserving decomposition if possible? So I could not find it actually. I've already tried this. Okay. I wanted to check whether some information is given about it or not, but I could not find this information. So the BCNF decomposition algorithm that we have seen, okay, that will definitely give you lossless BCNF, but will it give you dependency preservation whenever possible? Of course, whenever possible, will it give you dependency preservation? That is what you are asking, right, Mavit? Right? So whenever possible, whenever dependency preservation is possible, will it give you dependency preservation? Okay. This information is not available on the internet. I tried this. Okay. So I studied all the standard books, every standard book I studied, but still I could not find this information. Okay. Is this clear? But anyway, I think you don't have to worry about it. Okay. So basically, in the GATE exam, only simple question will be given to you. And for that simple question, this is my suggestion. This is my suggestion. You just apply this algorithm. Okay. This lossless BCNF algorithm you apply. That's it. Just apply this algorithm. Okay. And you don't have to worry about anything else. Just apply this algorithm. Okay. Mavit, is this clear? So actually in the standard resources, in all the standard resources, I found, I think 30 or 40 standard resources I studied, but this information I could not find. Okay, so that is the reason I'm just, this is my suggestion from, this is my suggestion to you, that just apply this BCNF decomposition algorithm and don't worry about anything else. Okay, there is a GATE question on this topic. That question we will solve. Okay, any other doubt? Is this concept clear? This is your normalization over. In the normalization, every topic, everything is over. Not even a small topic is remaining. Okay, not even I can say not even this is remaining. Not even this topic is remaining. Okay, everything is over. So your normalization completely over. Okay. So now, actually, I wanted to complete this. I wanted to finish this because anyway, this was pending for few days. So this was pending. So that is the reason I just wanted to finish this. Now you can say that, okay, normalization is over. ER model is over. Queries is over. Okay. SQL, TRC, relational algebra, ER model and normalization, relational model. So all these topics are over, completely over. Okay. And you can try the gate questions now. For all these topics, try the gate questions. And tomorrow we will start file organization and indexing, and then transaction management. Okay. Tomorrow and day after tomorrow. I think 3 days it will take. File organization and indexing. It will take almost 3 days. Okay. So I think after 3 days, we will start transaction management. Okay. Any doubt, anyone? Please tell me. Okay. Everything is clear? Okay. So tomorrow morning, you have compiler design class, SDT. SDT class is there. So tomorrow morning. Okay. And DBMS class will be in the evening. Tomorrow is Sunday. Do we have Sunday tomorrow? Okay. So attempt the test. Queries test we will discuss tomorrow. Okay. Queries. Tomorrow Sunday or Saturday? Okay, Saturday. So on Sunday, we will discuss the queries test. The Go classes test series, queries test, live discussion we will do in the on Sunday. Tomorrow we will have live class. Indexing we will study. Indexing and file organization we will study from 8 p.m. Okay. Okay. Thank you, everyone.